Imagine a peculiar truth that challenges everything we think we know about reality. What if the mere act of observing something could halt its natural decay, preventing it from ever truly changing? In our grand familiar world, our gaze is a neutral thing, incapable of stopping a flower from wilting or a star from exhausting its fuel. Yet deep within the universe's most fundamental fabric, the rules are astonishingly different, suggesting an active, even defining role for our attention. How could a simple act of looking possess such profound power over the very flow of existence? We stand often unawares upon a grand stage of magnificent certainty. The sunrise arrives reliably each morning, a tossed coin descends predictably, and the very ground beneath our feet feels steadfast, unyielding. Our everyday lives are governed by the comforting, familiar rules of classical physics laws that dictate the motion of planets, the flow of rivers, and the simple mechanics of a ball rolling down a hill. This is the macroscopic world, the realm of the tangible, where cause and effect are clear and our intuition serves us well. We build our understanding, our technologies, and our civilizations upon this bedrock of predictable outcomes. Yet just as the visible peak of an iceberg hints at colossal depths unseen, our familiar reality is merely the uppermost layer of something far more complex, more bizarre, and profoundly active. Beneath the surface of every solid object, every pulse of light, every fleeting moment of time, lies a hidden architecture, a foundational fabric of existence woven from rules that defy our common sense. It is a realm where certainty gives way to probability, where particles behave as both waves and discrete entities, and where the act of observation itself becomes an astonishing transformative force. Welcome to the quantum realm, a bizarre landscape where the very fabric of existence behaves in ways that baffle even the most seasoned physicists. Here, the simple, reassuring certainties of classical physics vanish, replaced by a strange tapestry woven from probabilities, paradoxes, and unsettling dualities. A particle is no longer a tiny, predictable billiard ball. It is a ghost simultaneously everywhere and nowhere, a mere potentiality, until it is somehow coaxed into revealing itself. Imagine trying to predict the exact path of a single electron. In our macroscopic world, such a task for a falling apple is trivial. But in the quantum domain, an electron might choose any path, or perhaps even all paths, until we attempt to pin it down. This is why our common sense often fails us here. The rules that govern the universe at this scale are profoundly counterintuitive. They demand that we abandon our preconceived notions of how things should work and embrace a deeper, stranger truth. This is a place where phenomena defy direct observation, existing in a shadowy state of uncertainty, forcing us to redefine what we mean by real. It is a mysterious frontier, beckoning us to understand its unique logic. One of the most profound revelations from our dive into the quantum realm is the discovery that the fundamental constituents of our universe, light and matter, possess a perplexing split personality. For centuries, we understood light purely as a wave rippling through space, like waves on an ocean, creating interference patterns and diffracting around obstacles. Yet revolutionary experiments unveiled a startling truth. Light also arrives in discrete packets of energy individual particles we call photons, like tiny indivisible bullets of illumination. It's as if the ocean waves could suddenly transform into individual droplets. This inherent duality doesn't stop with light. Even more astonishing, the very building blocks of matter, electrons, protons, and neutrons, those seemingly solid, distinct particles also exhibit wave-like properties. An electron, long conceived as a minuscule sphere orbiting an atomic nucleus, can under specific circumstances behave like a spread-out wave interfering with itself, as it moves much like sound waves interacting in a room. It is a chameleon of the cosmos, shifting its identity based on how we choose to interact with it. This wave-particle duality is not a convenient approximation. It is the intrinsic nature of existence at the quantum scale. It means that an electron isn't just a particle or a wave. It's a quantum entity that manifests as one or the other depending on the experimental setup, like a performer who can be both a soloist and part of a grand synchronized dance. We, the observers, are implicitly part of this unfolding reality. This unsettling truth demands a complete re-evaluation of what we mean by thing or object at the foundational level. How can something be both a distinct point and a diffused ripple simultaneously? And what does this bizarre flexibility imply about the very act of observation? If the wave-particle duality stretches our understanding of what a thing can be, then the principle of superposition truly pushes the boundaries of imagination. In our everyday lives, an object is always in one definite state. A coin is either heads or tails. A light switch is either on or off. A cat is either asleep or awake. But in the quantum world, before we observe it, a particle can exist in all its possible states simultaneously. It is not choosing one or the other. It is genuinely inhabiting every option, like a phantom blurring through walls, existing everywhere and nowhere all at once until something forces it to settle. Consider a tiny electron. Before any interaction, this electron is not just in one place. It is remarkably spread out across its entire potential path, existing as a fuzzy cloud of probabilities, a ghost of itself inhabiting multiple locations at the very same instant. It also holds all its possible energy levels and spin orientations concurrently. This is not merely a lack of knowledge on our part. It is the fundamental reality of the electron itself. It exists in a superposition of states, a blend of all possibilities, a tapestry of potential realities, interwoven into a single quantum entity. This concept feels deeply counterintuitive because we have no macroscopic equivalent. You never see a car simultaneously in your driveway, at the grocery store, and on the highway. Yet for a quantum particle, this multi-state existence is its default. It is a fundamental property of the quantum realm, illustrating how incredibly delicate and responsive these systems are to any form of probing. This bizarre ability to hold multiple realities at once is not just a curiosity. It is a powerful computational resource, forming the bedrock of technologies we are only just beginning to grasp. But how does this elusive phantom, this blend of potentials, resolve itself into the singular definite reality we perceive? To truly grasp the strangeness of superposition, we must picture a quantum particle not as a tiny solid dot, but as a diffuse, hazy swirl of potential. Imagine, if you will, the scent of fresh baking wafting through a house. You know it's somewhere in the air, a presence felt in many rooms at once, but its precise origin remains elusive until you follow the aroma to the kitchen. Similarly, a quantum particle, before it is observed, exists as a cloud of possibilities. A probability wave spread across space, embodying every location or energy state it could occupy. This isn't merely a vague idea. It's formally described by what physicists call the wave function, a mathematical description of all potential outcomes for a quantum system. It outlines the likelihood of finding the particle in any given state. So an electron isn't here or there. It's in a shimmering, undecided state, more like a cosmic whisper of where it might be than a tangible object. This undecided presence is its natural, most stable form when left undisturbed by the macroscopic world. This fundamental uncertainty is what makes the quantum realm so profoundly different from our everyday experience. We are accustomed to seeing objects with clear positions and definite properties. But in the subatomic world, such clarity is absent until an interaction occurs. The particle dances in a realm of pure potential, a ballet of countless futures existing simultaneously within that fuzzy probable cloud. It is a profoundly elegant yet baffling state of being. But what force then compels this swirl of possibilities to coalesce into a single, undeniable reality? Having explored the astonishing reality of superposition, where quantum particles exist as a vibrant swirl of possibilities, a profound question inevitably arises. How does this hazy potential coalesce into the single definite reality we perceive? The answer lies in perhaps the most unsettling discovery of the quantum realm, the act of observation itself. In our everyday macroscopic world, observing something is a passive act. If you look at a tree, the tree remains a tree unaffected by your gaze. Your eyes simply gather light reflecting from an already existing solid object. But in the quantum domain, this fundamental assumption crumbles. Here, an act of looking and interaction, a measurement of any kind, fundamentally alters the system being observed. It's as if peering at a perpetually shifting kaleidoscope suddenly forces all its colored fragments to snap into one fixed, unchangeable pattern. This is the central mystery, the core enigma that has puzzled physicists for a century. When a quantum particle existing in a superposition of states, simultaneously in multiple places or possessing multiple energies, is measured, it instantaneously chooses one of those possibilities. The spread-out probability wave, the cloud of possibilities we discussed, instantly collapses into a single concrete reality. We don't just find out what state the particle was in, our interaction appears to determine its state. This isn't merely discovering a hidden truth. It's a process of active revelation where the observer, by the very act of interaction, participates in shaping the reality of the particle. Imagine a lottery ticket that holds all possible winning numbers until you scratch it, at which point it reveals only one. That moment of scratching is the quantum measurement. It forces the universe to commit. This unsettling influence of our attention, this profound alteration caused by simply looking, is a cornerstone of quantum mechanics, and it begs a deeper investigation into our own role in the cosmic drama. We stand at the precipice of a revelation, one that redefines our place in the cosmic tapestry. If, as we have seen, the quantum particle exists as a swirling miasma of possibilities, a probability wave without fixed form until our interaction, then what does that truly say about the nature of reality? Chapter after chapter, we have peeled back the layers, moving from the predictable dance of classical mechanics to the strange ballet of the subatomic. And with each step, the observer and entity often relegated to the background steps, further into the spotlight. It is here that the fundamental unsettling truth emerges, not as a whisper, but as a resounding chord that vibrates through the very core of our understanding. We grapple with the dizzying notion that our very gaze, our act of seeking information, of measuring, of simply knowing, might not merely reveal what is already there, but actively participate in bringing it into being. Consider the implications. In our macroscopic world, the chair sits there, solid and undeniable, whether we look at it or not. The moon hangs in the night sky, its existence independent of our perception. Classical physics assures us of an objective external reality that rolls on indifferent to our presence. But the quantum realm shatters this comfortable illusion. Here the particles spin its position, its momentum. These are not inherent properties awaiting discovery. They are, in a profound sense, indeterminate potential until an act of observation forces them to choose. This is not to say that the universe springs forth from our minds or that reality is a figment of human imagination. Rather, it suggests a deeper, more intricate dance between consciousness and existence, between the act of knowing and the state of being. The observer is not necessarily a human eye. It is any interaction that extracts information, any system that measures. It could be a photon bouncing off an electron, a detector registering a particle's trajectory, or even the subtle entanglement with another particle that forces a definite state. Yet the conceptual weight of the observer inevitably loops back to us, the conscious beings who build the detectors, who interpret the data, who construct the theories. The discovery is this: we are not merely passive spectators in the grand cosmic drama. Our role is active, transformative, and profoundly intertwined with the fabric of reality itself. It forces us to confront an unnerving question. If our inquiry shapes the very reality, we investigate how objective can our understanding truly be. The clear line between the observed and the observer blurs, then dissolves. We stand not outside, but within the quantum experiment, our collective gaze, a silent, potent force that sculpts the formless into form, possibility into actuality. This fundamental realization that our interaction with the subatomic world is not neutral but formative truly challenges the bedrock of what we thought we knew about existence. Our journey into the quantum realm has unveiled a profound truth. The act of observation is not a passive glance, but an active participation in shaping reality. Yet this radical notion, this defiance of common sense, echoes back through history, revealing a timeless human struggle with the nature of motion, time, and existence itself. We leave the flickering screens of quantum laboratories for a moment and travel back 2.5 millennia to the sun-drenched philosophical schools of ancient Greece. It is there in the city of Elea that we encounter Zeno, a philosopher whose cunning arguments still ripple through the ages, challenging our most intuitive beliefs. Zeno of Elea crafted a series of paradoxes, mind-bending puzzles designed to demonstrate the inherent contradictions in the concepts of motion and plurality. While many of his thought experiments persist, one in particular strikes us with chilling relevance to our quantum revelations: the paradox of the arrow. Imagine an arrow loosed from a bowstring arcing gracefully through the sky. For Zeno, the puzzle unfolds like this: at any given instant in its flight, the arrow occupies a space exactly equal to itself. If it occupies a space equal to itself, it must at that precise instant be at rest. It cannot be moving to move. It would need to occupy more space than itself. But if the arrow is at rest at every single instant of its flight, how can it ever traverse any distance? How can it ever truly move? By this logic, motion becomes an illusion, an impossibility woven from an infinite series of static moments. This is not a simple trick of words, nor a mere intellectual game. Zeno's arrow is a profound philosophical quandary, one that directly challenges our intuitive understanding of continuous motion, the nature of time, and the infinite divisibility of space. It forces us to confront the limitations of our perception and the paradoxes that emerge when we attempt to dissect reality into infinitesimal points. In essence, Zeno's argument invites us to observe the arrow at an infinitesimally small interval of time to take a conceptual snapshot of its position. And in that very act of defining its location at an instant, we inadvertently freeze its motion. The arrow is at point A, then at point B, then point C, each a distinct stationary point. The very act of pinpointing its location, of making it definite at any given moment, seems to strip it of its capacity for change, for progress. This ancient paradox, born from the cradle of Western thought, unwittingly sets the stage for a much later, much stranger scientific revelation, echoing the unsettling power of the observer in the quantum world. Our journey into the quantum realm has illuminated the profound active role of observation. Now we turn back to the ancient world to truly lean into the perplexing logic of Zeno's arrow, for it presents a logical dilemma that mirrors the challenges we face today in understanding the very nature of existence and change. We are tasked with unpacking how, in Zeno's thought, an arrow seems to become irrevocably frozen in time. Recall the premise. An arrow in mid-flight occupies a space exactly equal to itself at any given instant. If it occupies a space equal to itself, it is by definition at rest at that precise moment. It is not in the process of moving for to move. It would need to occupy a larger space, or be in the act of transitioning, which defies the idea of an instant. So for that infinitesimally brief slice of time, the arrow is utterly undeniably still. This is where the paradox tightens its grip. If the arrow is at rest at every single instant throughout its entire flight, how can it ever cover any distance? How can it ever actually arrive at its target? If every constituent moment of its journey is a state of stillness, then motion itself seems to dissolve into an illusion. The logical consequence is jarring the arrow, despite our common sense, never truly moves. It exists as a continuous series of static points, each a snapshot of non-motion forming a sequence that somehow bafflingly never adds up to actual progression. The dilemma is not merely academic. It strikes at the heart of our intuitive understanding of continuous motion. Zeno forces us to confront the uncomfortable truth that when we attempt to dissect movement into its constituent moments, when we observe its position at an infinitesimal interval, we inadvertently strip it of its capacity for change. The act of pinpointing its location, of making it definite at any given moment, seems to negate its dynamism. Our mental gaze upon the arrow in this thought experiment freezes it. This ancient puzzle challenges the very notion of how change occurs over time. It suggests that if reality is composed of discrete static points, then the smooth flow of continuous motion becomes impossible. The arrow held under Zeno's logical microscope ceases its flight. It highlights a profound vulnerability in our perception. Our attempts to precisely define a state can seemingly inhibit its evolution. This is the unsettling core of the paradox, a logical quandary that halts motion not physically, but conceptually, setting the stage for a parallel, far stranger phenomenon in the quantum world. We have lingered in the ancient world grappling with Zeno's arrow, a conceptual enigma that suggests motion can be halted by mere observation. Now we pull back the veil of millennia and see that this ancient paradox finds a startling, profound echo within the very heart of the quantum realm. What Zeno explored as a philosophical trick of logic quantum physics uncovers as a fundamental physical reality. The connection is striking, almost unnerving. Zeno's arrow, observed at every infinitesimal instant, becomes frozen, unable to progress. In the quantum world, we encounter a parallel phenomenon, a subatomic counterpart to this ancient riddle. Here, a quantum system left unobserved evolves. Its wave function spreads, its possibilities multiply, and it progresses towards a new state or decays from an unstable one. But what happens if we apply Zeno's method? What if we continuously or repeatedly observe it? Imagine a quantum particle, for instance, a radioactive atom poised to decay. Its natural tendency is to transform, to move from one state of being to another. This process is probabilistic. It is not guaranteed at any given instant, but over time, the likelihood of decay increases. If we leave this atom alone, it will eventually decay, fulfilling its quantum destiny. Yet, if we continuously monitor it, if we frequently check its state to see if it has decayed, something extraordinary occurs. Each time we perform an observation, the atom's probability wave collapses. It is forced to choose a definite state, either undecayed or decayed. If we find it in the undecayed state, which if we are checking frequently enough, will almost always be the case, we have, in a sense, reset its clock. By repeatedly observing it, we are continuously forcing it back into its initial undecayed state, preventing it from evolving. The more frequent our observations, the less time the particle has to progress towards decay. It becomes effectively frozen in its original state, just like Zeno's arrow. This is the unsettling heart of the matter. The active role of the observer, which we first uncovered as a shaper of immediate reality, now reveals itself as a potential inhibitor of change. An ancient thought experiment, once dismissed as a mere intellectual puzzle, now manifests as a measurable, reproducible phenomenon in the subatomic world. The philosophical paradox of motion being halted by infinite observation is reborn as a core principle of quantum dynamics, challenging our very understanding of time evolution and the subtle, profound influence of our gaze upon the universe. The conceptual freezing of an arrow finds its physical analog in the quantum realm, marking a profound convergence of ancient philosophy and cutting-edge science. We have traced a peculiar thread from the ancient world's philosophical puzzles to the enigmatic mechanics of the quantum realm. Zeno's arrow, a mere thought experiment, laid the groundwork for a truly astonishing phenomenon, one that challenges our deepest assumptions about time change and the very act of observing. We now arrive at the heart of this revelation, the capacity to halt quantum change, to freeze a system in its tracks simply by looking. This remarkable effect is known as the Quantum Zeno effect. It is the astonishing discovery that a quantum system left to its own devices will naturally evolve or decay, but if continuously or very frequently observed, it can be held in its initial state, its natural progression inhibited, almost as if time itself has been suspended for that particular particle. Imagine a quantum particle existing in a superposition, a cloud of possibilities. Without intervention, this superposition will eventually resolve into a definite state, or the particle will transition to another state through a process like radioactive decay. This evolution is governed by the laws of quantum mechanics, a probabilistic flow from one potential configuration to another. But then the observer steps in. Each time a measurement is performed on the system, its wave function, that spread of possibilities, instantaneously collapses into a single definite reality. If the measurement is frequent enough, and if the system is found to be in its original state, which is overwhelmingly probable if measurements are rapid, then it is immediately forced back into that state. It is as if every split second we are pulling the system back from the brink of change, resetting its quantum clock to zero. Consider the radioactive atom we discussed earlier. Its probability of decaying increases over time. If we check it once every hour, it has 60 minutes to evolve towards decay. But what if we check it every microsecond? Every time we find it undecayed, it collapses back into the undecayed state, effectively preventing the probability distribution for decay from spreading out significantly. The sheer frequency of observation acts as a constant subtle intervention, nudging the system back to its starting point. This is the profound discovery that shifts our understanding. The act of observation is not merely a witness to change, it can become a powerful deterrent against it. The continuous gaze of measurement, far from being passive, actively stabilizes the quantum system, holding it fast against its inherent tendency to transform. It is as if the universe, when intently watched, sometimes pauses its internal clock, revealing an uncanny power that resides within the observer's very presence. The dynamic flow of quantum evolution is not just revealed by our instruments, it can be arrested by them. This ability to hold quantum change at bay, to exert such a direct influence on the fundamental processes of matter, represents a startling expansion of our scientific grasp. We have grasped the astonishing power of the Quantum Zeno effect, the ability of constant observation to freeze a quantum system in its initial state. But how does this truly work? What is the fundamental mechanism by which our repeated gaze or any interaction that extracts information prevents change at the subatomic level? This is where the core machinery of the effect truly reveals itself, offering a profound insight into the mechanics of quantum reality. Recall that a quantum particle left to itself does not simply jump from one state to another. Instead, its wave function, its cloud of possibilities, evolves. For a radioactive atom, this means the probability of it decaying into a different element slowly but surely spreads, increasing over time. Imagine this as a smooth, continuous growth in the likelihood of a transition occurring. The atom is not yet decayed, but it is moving probabilistically towards that future state. Here is the key discovery of the mechanism. The act of measurement fundamentally alters this smooth evolution. Each time we perform a measurement, we force the quantum system to choose a definite state. It is no longer a spreading wave of potential. It is now unequivocally either in its original state or its decayed state. If we are monitoring a radioactive atom and we check it frequently, the overwhelming probability is that in the short interval between measurements, it has not yet decayed. So when we measure and find it in its original undecayed state, we instantaneously collapse its wave function back to that single point of certainty. The probabilistic evolution, which was just beginning to spread its tendrils towards decay, is abruptly cut short. It is as if we are resetting a quantum clock. The moment after our measurement, the wave function begins to spread again, starting its journey anew from the definite, undecayed state. This constant resetting is the heart of the Quantum Zeno effect. If the measurements are frequent enough, if we are checking the atom every microsecond, for instance, then the probability of it decaying between any two successive checks becomes vanishingly small. Each time we observe it, we pull it back from the threshold of change, effectively preventing the necessary probability for transition from accumulating. The particle simply does not have enough time between collapses to build up a significant chance of transforming. It is continually forced back into its original form, its evolution halted, its decay indefinitely postponed. The mechanism is not one of direct intervention to stop a process already in motion, but rather a repeated instantaneous return to the initial state, effectively keeping the system perpetually at the starting line of its potential transformation. We have peeled back the layers of the Quantum Zeno effect's mechanism, understanding how continuous observation resets the quantum clock. Now we confront the full startling impact of this phenomenon, the bizarre and counterintuitive ability to hold a quantum particle's natural progression entirely at bay. The discovery is this: a quantum system inherently designed to evolve to decay, to shift from one probabilistic state to another, can be rendered immobile in its quantum configuration. This is not simply a slowing down of change, but a profound suspension of its very tendency to transform. A particle poised for change, a system on the verge of transforming, finds itself locked in an unchanging embrace, not by external forces in the classical sense, but by the very act of its own constant scrutiny. Consider the case of the radioactive atom once more. Its internal quantum dynamics dictate a certain probability of decay over time. Without interference, This atom will eventually emit radiation and transform into a new element. This is its natural, inevitable progression. Yet with the application of the Quantum Zeno effect, we gain an astonishing level of control. By performing sufficiently rapid and frequent measurements, we effectively prevent the atom from ever reaching that decayed state. It remains undecayed indefinitely, held in a state of suspended animation relative to its decay process. The implications are vast and challenging to our intuition. We are accustomed to a universe where time marches forward, where processes unfold, and where change is an undeniable constant. But here at the quantum level, we discover a loophole, a means to arrest the flow of quantum evolution. The particle does not choose to stay in its original state. It is continually forced into that state by the interaction of measurement. Each probe, each photon directed at it, each piece of information extracted acts as an anchor, tethering it to its current reality and preventing it from drifting into its future possibilities. This ability to hold a quantum state immobile to effectively bypass its inherent probabilistic progression represents a monumental leap in our understanding and potential control over the fundamental building blocks of the universe. It is a direct demonstration of the observer's ultimate power, not just to define reality in a fleeting moment, but to enforce a prolonged, unchanging existence upon it. The universe, it seems, can be compelled to stand still, at least for a tiny quantum piece of itself, when subjected to the unrelenting gaze of measurement. This profound capacity to halt natural progression stands as one of the most remarkable discoveries in the quantum realm. We have journeyed through the unsettling power of observation, from Zeno's ancient arrow frozen in thought to the Quantum Zeno effect, where a system's evolution is held at bay by a persistent gaze. Now we arrive at the pivotal moment that underpins all these phenomena, the electrifying instant that transforms the ethereal quantum world into the concrete reality we perceive. This is the moment of wave function collapse, the precise juncture where a myriad of possibilities snaps into one definite state, like a profound, irreversible choice made within the fabric of existence. Before this moment, a quantum particle exists, not as a fixed entity, but as a probability wave, a smeared-out cloud of all its potential states. It might be spinning both clockwise and counterclockwise, or be in multiple locations simultaneously. This superposition is the very essence of the quantum realm's mystery, a state of profound indefiniteness, where every outcome is equally poised awaiting its cue. It is a universe of might-be, where reality is unwritten, held in a delicate balance. Then comes the interaction. An observer. Whether a human scientist with an instrument or a simple environmental particle engages with the quantum system. This engagement is more than just looking. It is a transfer of information, a forcing of the system to interact with something that embodies a definite state. And in that instantaneous interaction, the drama unfolds. The sprawling probability wave, the cloud of potential realities, does not simply shrink. It collapses. In that single dramatic instant, all but one of the possibilities vanish. The particle that was spinning both ways irrevocably chooses one direction. The particle that was in multiple locations now occupies only one. It is a swift, absolute transition from a state of boundless potential to a singular, undeniable fact. It is as if the universe, confronted by an act of observation, finally makes up its mind, selecting one specific outcome from the vast spectrum of what could be. This is the profound discovery. The moment of collapse is the bridge between the fluid, probabilistic quantum realm and our fixed classical experience. It is where potential becomes actual, where the abstract might be becomes the concrete is. The myriad of possibilities held within the probability wave does not slowly fade. It snaps instantaneously and irrevocably into a single definite reality. This dramatic, pivotal event, the collapse of the probability wave, is not just a theoretical construct. It is the very mechanism through which the act of observation sculpts reality, allowing us to interact with the quantum world and indeed to participate in its creation. We have journeyed deep into the quantum realm, a place where reality itself appears to shift and waver, where particles exist in a shimmering cloud of possibility until our gaze, our very act of observation, forces them into a single definite state. We have wrestled with Zeno's ancient paradox, seeing how the mere act of defining position at every instant conceptually freezes an arrow in its flight. And then we witnessed the astonishing convergence, the Quantum Zeno effect, where that ancient philosophical puzzle finds its physical counterpart in the subatomic world, demonstrating that repeated observation can indeed halt a system's natural evolution. But how do we truly grasp this profound concept? How do we wrap our macroscopic minds around the idea of observation acting as a cage holding quantum change at bay? Imagine, if you will, a playful, energetic puppy. Left to its own devices, this puppy would scamper, chase its tail, chew on a favorite toy, and eventually, after a burst of activity, curl up and drift off to sleep. This progression from play to rest is its natural probabilistic evolution. The puppy's state is constantly shifting, evolving towards sleep. Now, picture yourself as the diligent observer, the wakeful watchdog. Every time the puppy starts to yawn, every time its eyelids begin to droop, every time it settles down for a nap, you intervene. Perhaps you gently call its name, or offer a squeaky toy, or even just shuffle your feet. Your attention, your interaction snaps it back to full alertness. The puppy, constantly nudged, constantly brought back to its awake state by your persistent engagement, might never actually fall asleep. It is perpetually held in its initial wakeful condition, its natural progression towards rest, continually reset by your presence. This, we discover, is the essence of the Quantum Zeno effect. The quantum particle is our puppy. Its natural tendency to evolve, to decay, to transition into another state, its probabilistic journey towards a new reality, is akin to the puppy's inevitable drift towards sleep. Our measurement, our observation, acts as that relentless, wakeful watchdog. Each time we look, each time we interact with the quantum system, we are in effect snapping it back to its initial state. We collapse its evolving wave function, which carries the probabilities of all its potential future states, back to the starting point. It is as if the particle poised on the brink of transformation is violently pulled back by the very act of being examined. It cannot accumulate the necessary probability to transition, to decay, to truly evolve, because every moment it begins to move towards that new state. Our observational intervention drags it back. Our attention becomes a tether binding it to its current reality. The profound discovery here is not just that observation affects reality, but that it can actively prevent reality from evolving. The Quantum Zeno effect reveals our collective gaze, our very act of knowing, as a powerful stabilizing force capable of freezing the ephemeral dance of the quantum world. We have grasped the Quantum Zeno effect through the familiar image of a wakeful watchdog ceaselessly nudging a sleepy puppy back to alertness. This analogy helps us understand how observation can freeze a quantum system in its initial state, preventing its natural evolution. Yet this profound understanding did not spring forth fully formed from experimental apparatus. Long before the first particle was precisely manipulated to demonstrate this effect, brilliant minds were grappling with the theoretical underpinnings, daring to predict its existence through the sheer power of mathematics and logic. We journey back to a time when the strange implications of quantum mechanics are still being fully explored, when the behavior of the subatomic world continues to challenge classical intuition at every turn. In this intellectual landscape, two pioneering quantum theorists, Dr. George Sudarshan and Dr. B. Misra, emerge. They are wrestling with a fundamental question. What happens when a quantum system prone to decay or transformation is subjected to incredibly frequent observation? Their work is not about physically manipulating particles in a lab, but about abstract thought, about the elegant language of equations. They delve into the heart of quantum mechanics, examining the mathematical formalism that describes how a quantum state evolves over time. They understand that without external interaction, a quantum system follows a probabilistic path, its wave function spreading out, increasing the likelihood of transitioning into other states. But then they pose a critical question. What if this natural, uninhibited evolution is constantly interrupted? What if, at infinitesimally small intervals, we look at the system? Their theoretical calculations reveal something extraordinary. Each observation they deduce forces the system's wave function to collapse back to its initial measured state. If these measurements are performed with extreme rapidity, the system simply does not have enough time to accumulate the necessary probability to transition. It is like trying to cross a rapidly flowing river only to be repeatedly pulled back to the starting bank before you can make any real progress. Sudarshan and Misra, through rigorous mathematical proofs, formalize this astonishing prediction. They theorize that continuous rapid observation could indeed inhibit a quantum system's natural decay, effectively freezing its evolution. They publish their groundbreaking work laying out the precise conditions under which this phenomenon, which they implicitly link to Zeno's ancient paradox, should occur. This isn't mere speculation. It is a bold, testable hypothesis born from the very fabric of quantum theory. Their intellectual groundwork provides the crucial map indicating that the quantum Zeno effect is not just a philosophical curiosity, but an inherent, mathematically derivable consequence of the quantum world's fundamental rules. The challenge is now laid for the experimentalists: can this counterintuitive prediction be observed in the real, tangible universe? The theoretical stage for the quantum Zeno effect is set meticulously constructed by the pioneering minds of Dr. George Sudarshan and Dr. B. Misra. They have, through abstract thought and the elegant language of mathematics, predicted a phenomenon so counterintuitive it seems to defy the very nature of change. But a prediction, no matter how profound, often requires a formal declaration, a public unveiling that solidifies its place in the scientific discourse. This arrives decisively in 1977. In that year, Sudarshan and Misra publish their pivotal paper, The Zeno's Paradox in Quantum Theory. This is more than just another academic article. It is a meticulously crafted document that formalizes the quantum analogy to Zeno's ancient puzzle. Within its pages, they meticulously lay out the mathematical framework, demonstrating precisely how repeated rapid measurements can indeed inhibit the natural evolution or decay of an unstable quantum system. Their argument is steeped in the fundamental principles of quantum mechanics, particularly the role of measurement and wave function collapse. We recall that a quantum particle exists as a probabilistic wave, a cloud of possibilities, until an observation forces it into a single definite reality. Sudarshan and Misra build upon this, showing that if these observations occur frequently enough, if the wakeful watchdog of measurement is truly vigilant, the system is perpetually reset. Each look forces the wave function back to its initial state, erasing any progress it might have made towards evolving or decaying into a different state. The probability of transition, which builds up over time between measurements, is simply given no chance to accumulate to a significant degree. This paper is a landmark. It transforms what might have been considered a mere intellectual curiosity into a robust, testable scientific hypothesis. Sudarshan and Misra are not just musing about the quantum world, they are providing the precise mathematical equations and conditions under which this freezing effect should manifest. They attribute the term Quantum Zeno effect directly to their work solidifying its place in the lexicon of quantum physics. Their work challenges the very notion of time and change within the quantum realm. It suggests that our interaction with the universe, far from being a passive act of discovery, can actively dictate the progression of fundamental processes. The paper serves as an intellectual beacon, a clear theoretical blueprint that dares experimental physicists to step into the lab and attempt to observe this extraordinary phenomenon in action. The gauntlet is thrown. The challenge is laid before the world's most precise instruments, and ingenious experimentalists can the quantum Zeno effect so elegantly predicted on paper truly be brought forth into tangible reality. We stand at a precipice looking back at the intellectual edifice built by Sudarshan and Misra, their pivotal 1977 paper, a testament to the predictive power of theoretical physics. But what truly underscores the genius of their work, and indeed the audacity of quantum mechanics itself, is that these profound conclusions, this foretelling of a quantum freeze, were reached long before a single empirical verification. This was not a response to an anomaly observed in a laboratory. It was a bold declaration born from the very heart of mathematical reasoning. In the nascent decades of quantum mechanics, the scientific community grappled with phenomena that defied classical understanding. Superposition entanglement, wave-particle duality. Each concept forced a radical re-evaluation of reality. Yet even within this landscape of the bizarre, the idea that mere observation could halt the natural progression of a particle's state, essentially freezing time for a subatomic entity, was a truly audacious proposition. It required an unwavering faith in the underlying equations, a conviction that if the math led to such an improbable outcome, then that outcome must in fact be possible. Sudarshan and Misra, armed with their rigorous mathematical derivations, effectively peered into the future of quantum experimentation. They predicted with striking confidence that if one could measure an unstable quantum system with sufficient frequency and precision, its inherent tendency to decay or transform would be suppressed. They weren't just describing what might happen. They were outlining a specific, testable effect, a direct consequence of the continuous collapse of the wave function under persistent scrutiny. Imagine the intellectual courage required to make such a claim. To assert that an atom prone to radioactive decay could effectively be rendered stable simply by watching it intensely, or that a particle destined to transition into another energy state could be held indefinitely in its current configuration by an unending series of observations. These were not minor adjustments to existing theories. These were profound statements about the active role of observation in shaping quantum reality, pushing the boundaries of what was considered plausible. Their prediction was a lighthouse in the theoretical seas, guiding future experimentalists towards an astonishing truth. It suggested that human interaction, even at its most fundamental level, was not merely a passive recording of pre-existing facts, but an active dynamic force capable of influencing the very flow of quantum time. The challenge laid bare by Sudarshan and Misra was immense to bridge the chasm between their elegant equations and the messy reality of the laboratory. It was a call to arms for experimental physicists, an invitation to prove or disprove the existence of this foretold quantum freeze. The stage was now set not just for understanding, but for validation. The bold prediction by Sudarshan and Misra, articulated in their landmark 1977 paper, hangs in the air a theoretical marvel awaiting its tangible proof. They have foretold a quantum freeze, an almost mythical ability for observation to suspend the very evolution of subatomic reality. But moving from the elegant precision of mathematics to the messy complexities of the laboratory presents an immense challenge, sparking a determined scientific race across the globe. Experimental physicists, driven by a blend of skepticism and profound curiosity, are confronted with a daunting task. How do we build a system that can reliably trap and interrogate individual quantum particles? How do we observe them so frequently that their natural progression is halted without the act of observation itself destroying the delicate quantum state? This is the core confrontation, the clash between the theoretical ideal and the practical limitations of technology at the atomic scale. The stakes are high. If the Quantum Zeno effect can be empirically verified, it will not only affirm a startling aspect of quantum mechanics, but also unlock new avenues for quantum control, potentially revolutionizing future technologies. This prospect ignites a fervor in laboratories worldwide. Researchers begin to conceptualize and construct intricate setups, each vying to be the first to capture this elusive quantum phenomenon. The requirements are extreme. We need ultra-high vacuum chambers to isolate a particle from any stray environmental interference, as even the slightest interaction can cause an uncontrolled wave function collapse. We need sophisticated laser systems capable of cooling particles to near absolute zero, slowing their motion to a crawl so they can be precisely manipulated. Most critically, we need detection methods that can perform repeated, non-destructive measurements with incredible speed, far faster than the natural decay rate of the chosen quantum system. Imagine trying to photograph a hummingbird's wing beat, but instead of just one click, you need thousands per second, and each click must somehow prevent the bird from flying away. Scientists dedicate countless hours meticulously refining their techniques, pushing the boundaries of what is technologically feasible. They grapple with the inherent fragility of quantum states, striving for longer coherence times, where a particle can maintain its quantum properties without decohering. Every component, every laser pulse, every magnetic field must be perfectly calibrated. It is a grueling, precise hunt for empirical evidence, a testament to humanity's relentless pursuit of understanding the universe's most fundamental rules. The theoretical blueprint is clear. Now the monumental task of constructing the physical manifestation of this bizarre truth falls to the experimental pioneers who embark on their rigorous quest to bring the quantum freeze from prediction into observable reality. The theoretical prediction of the Quantum Zeno effect by Sudarshan and Misra has ignited a fervent race to prove its existence. But before we can observe this quantum freeze, experimentalists face a monumental hurdle. How do we even begin to isolate and precisely control something as fleeting and infinitesimally small as a single quantum particle? In our macroscopic world, we grasp objects with our hands, contain them in jars. At the quantum scale, such direct manipulation is impossible. This demands a level of ingenuity that pushes the very boundaries of engineering and physics. The solution we discover lies in the ingenious methods developed to hold these tiny atoms in perfect isolation, suspended in a void where they can be observed without interference from the chaotic environment around them. We are talking about particles so minute, so delicate, that even a single stray air molecule or a faint thermal vibration can disturb their quantum state. The key lies in selecting the right subject, not just any atom, but an ion. An ion is an atom that has gained or lost one or more electrons, giving it an electric charge, and a charge we know responds to electric and magnetic fields. This fundamental property becomes the very handle experimentalists need. Imagine crafting an invisible cage made not of solid bars, but of precisely tuned electromagnetic fields. This is the essence of an ion trap. Within these traps, a single ion, perhaps a beryllium ion, is levitated, held perfectly still in space by the carefully balanced forces of these fields. It is a technological marvel, an almost unbelievable feat of precision engineering to create an environment where a solitary atom can be held captive away from the jostling thermal noise of the laboratory. Yet merely trapping an ion is not enough. These atoms, even when isolated, are still buzzing with thermal energy jiggling wildly, which introduces unwanted quantum noise. To truly control and observe their quantum states, we must bring them to a near standstill. This leads to another brilliant innovation: laser cooling. By firing precisely tuned laser beams at the trapped ion, scientists exploit the momentum of photons. Each time a photon from the laser beam is absorbed and re-emitted by the ion, it imparts a tiny kick. By tuning the laser frequency just right, these kicks preferentially slow the ion down, effectively chilling it to temperatures just fractions of a degree above absolute zero. At these frigid temperatures, the ion's motion is drastically reduced, making it an incredibly stable and controllable quantum system. These ingenious methods, the precision of ion traps, and the chilling power of laser cooling transform what seems an insurmountable obstacle into a tangible pathway. They represent the foundational steps, the necessary prelude to any experiment aiming to probe the Quantum Zeno effect. Without the ability to reliably isolate and prepare a single undisturbed quantum particle, the phenomenon would remain forever confined to the theoretical realm. The race is on, and the tools are being forged to finally bring the abstract predictions of quantum mechanics into the clear light of empirical observation. The abstract predictions of Sudarshan and Misra, so audacious in their mathematical elegance, have hung in the balance, challenging experimentalists across the globe. We have seen the incredible lengths scientists go to developing technologies like ion traps and laser cooling merely to isolate a single quantum particle. Now, in the year 1990, at the National Institute of Standards and Technology (NIST), a pivotal moment arrives. Here, Dr. David Weinland, a name that will become synonymous with precision quantum control, leads a team poised to bridge the chasm between theory and reality. Weinland's laboratory is a symphony of cutting-edge technology, ultra-cold vacuum chambers, precisely tuned lasers, and sophisticated detection systems. Their chosen subject for this landmark experiment is a single beryllium ion held captive and chilled to near absolute zero within a meticulously crafted ion trap. This beryllium ion, a charged atom, possesses distinct internal energy states, and the team prepares it in a specific initial state, ready for a quantum leap. The experiment is designed to test the very core of the Quantum Zeno effect. The beryllium ion is initially prepared in a state from which it is meant to spontaneously transition to another lower energy state. If left undisturbed, this transition would occur naturally over a predictable period. This spontaneous decay is the quantum equivalent of our puppy naturally drifting off to sleep. But Weinland's team introduces a twist. They apply a series of precisely timed, very rapid laser pulses. These are their measurements to the beryllium ion. Each pulse is specifically designed to probe whether the ion has transitioned to the new state. This is the wakeful watchdog's incessant nudge. If the ion is still in its initial state, it interacts with the laser light in one way. If it has transitioned, it interacts differently. The crucial point is that each interaction, each look, acts as a quantum measurement collapsing the ion's wave function. The results are electrifying. When the beryllium ion is left unobserved, it transitions to its lower energy state as expected. However, When Weinland's team introduces the rapid repeated laser pulses, they observe a dramatic suppression of this transition. The more frequently they look at the ion, the less likely it is to decay. The ion caught in the relentless gaze of the experimental apparatus is held effectively frozen in its initial unstable state. Its natural probabilistic progression is halted reset with each measurement, just as Sudarshan and Misra predicted. This is a triumphant discovery. The 1990 experiment using a single beryllium ion provides the first direct and unambiguous empirical verification of the Quantum Zeno effect. It is a resounding affirmation of quantum mechanics and a testament to the power of human ingenuity. The theoretical concept, once confined to equations and abstract thought, is now undeniable, proven in the tangible reality of a laboratory. The quantum freeze is real, and its implications for controlling and manipulating the quantum world begin to unfold. We have established Dr. David Weinland's groundbreaking 1990 experiment, a pivotal moment confirming the Quantum Zeno effect. This triumph relied not only on the ability to isolate and cool a single beryllium ion, but on an equally remarkable feat, the delicate process of shining light upon this infinitesimally small entity to determine its exact quantum state, all without disrupting the very phenomenon they sought to observe. Consider our beryllium ion, nestled in its electromagnetic trap, chilled to a mere whisper above absolute zero. Like all quantum particles, it possesses discrete energy levels, specific rungs on an atomic ladder. For the Quantum Zeno effect experiment, two of these states are critical: an initial higher energy state, from which the ion is prone to decay, and a lower stable state it would transition into if left unperturbed. The challenge is to see which state the ion is in at any given moment to apply that wakeful watchdog gaze. This is where precisely tuned laser light becomes our eyes into the quantum realm. To determine if the beryllium ion is in its initial unstable state, scientists direct a laser beam, a stream of photons with a very specific energy towards it. This laser is tuned to a frequency that only the initial higher energy state can absorb. If the ion is in this state, it will readily absorb these photons, briefly jump to an even higher fleeting energy level, and then quickly fall back, emitting a photon of light as it does so. This emitted light, a tiny flash of fluorescence, is then meticulously collected by sensitive detectors. A click of photon detected signifies the ion is indeed in its initial state. But what if the ion has decayed into its lower stable state? If it has made that spontaneous quantum leap, then when the same laser light is shined upon it, nothing happens. The laser photons are simply ignored. There is no absorption, no re-emission, no click from the detector. The absence of a photon signals that the ion has transitioned. This difference, the presence or absence of emitted light, provides the immediate, unambiguous measurement of the ion's state. This process is delicate not only because of the minuscule scale, but because each interaction, each absorption and emission is a form of observation that collapses the ion's wave function. For the Quantum Zeno effect, this collapse is precisely what prevents the ion from accumulating the probability to decay. By repeating these laser probes with extreme rapidity before the ion has a chance to naturally transition, the researchers continuously reset its state back to the initial unstable one. Each peak forces the decision: are you still here in your original state? And if the answer is yes, indicated by the emitted photon, the ion is confirmed, and its journey towards decay is effectively halted, pulled back to the starting line. This ingenious use of light allows us to both interrogate and control the very fabric of quantum reality. We have witnessed the ingenious setup of Dr. David Weinland's team from the isolation of a single beryllium ion to the delicate art of peering into its quantum state with precisely tuned laser light. Now we arrive at the culmination of their efforts, the direct, unambiguous demonstration of the Quantum Zeno effect, proving the astonishing ability to stop an atom from spontaneously changing its energy level. Imagine our beryllium ion prepared in its initial unstable state. This state is akin to a ball perched precariously at the top of a hill. Given enough time, gravity would inevitably pull it down to a stable resting place at the bottom. For the beryllium ion, this gravity is the natural quantum probability of decay, the inherent tendency to spontaneously transition to a lower, more stable energy state, emitting a photon in the process. If Weinland's team were to simply prepare the ion and then walk away, returning after a specific period, they would find it had indeed made that quantum leap about half the time. This is its natural, unobserved evolution. But this experiment introduces the relentless, wakeful watchdog of repeated observation. The team bombards the beryllium ion with a rapid succession of very short, precisely timed laser pulses. These are their measurements to the beryllium ion. Each pulse is designed to ask the same critical question: are you still in your initial unstable state? If the ion is still in its initial state, it responds to the laser pulse by briefly absorbing a photon and re-emitting a tiny flash of light that registers on the detectors. This detected flash is the confirmation: yes, I am still here in the initial state. Critically, this very act of confirmation, this observation, forces the ion's wave function to collapse back to that initial state. It is as if the ball, having begun to roll down the hill, is instantaneously lifted back to the very peak by an unseen hand. If, however, the ion had managed to spontaneously decay into its stable state. Between two pulses, it would not respond to the laser. No photon would be absorbed, no light would be emitted. The absence of a click from the detector would signal that the ion had indeed transitioned. But this is precisely what the repeated measurements prevent. What the experiment reveals is profound. When the laser pulses are applied frequently enough faster than the ion's natural decay rate, the number of observed decays plummets dramatically. The beryllium ion, despite its inherent instability, is found overwhelmingly in its initial high-energy state. It cannot make the quantum leap to the lower state, because every time it begins to develop the probability to do so, an observation collapses its wave function, resetting it to its starting configuration. It is caught in a perpetual loop of observation and reset. This is the direct, compelling evidence. The very act of peering at the beryllium ion, of continuously asking about its state, actively halts its natural progression. Weinland's team has not just verified a theoretical prediction, they have demonstrated the extraordinary power to prevent a quantum system from spontaneously changing its energy level. The quantum freeze is not just a concept, it is a demonstrable reality, a testament to the profound and active role of observation in the subatomic world. We stand with Dr. Weinland's team witnessing a triumph that redefines our relationship with the smallest constituents of reality. The beryllium ion, a lone cosmic dancer, is held captive, yet exquisitely free within its electromagnetic cage, poised on the precipice of its natural evolution. Its inherent inclination is to transition, to spontaneously shift its energy state, to decay into a different configuration. This is the quantum dance it desires, to perform its probabilistic trajectory, unfolding towards a new form. Yet we, the collective observer guided by the meticulous hands of the quantum engineer, stand poised to intervene. Through an ingenious arrangement of precisely tuned laser light, the team doesn't merely look at the ion, they perform an act of constant quantum interrogation. Each rapid pulse, each flicker of light that ascertains the ion's current state, acts not as a passive glance, but as an active intervention, an instantaneous reset. It is a query answered with an immediate, profound revelation: the ion is ein, still in its initial state. This unwavering, unrelenting vigilance is the true marvel of the Quantum Zeno effect in living action. Imagine a tireless sentinel, an ever-present guardian standing watch over a delicate, fleeting whisper. Every time that whisper begins to fade, to morph into something new, the sentinel shouts, "Not yet, be what you were." And the whisper, compelled by the very quantum laws we have tirelessly worked to unveil, snaps back to its original predefined form. The beryllium ion, subjected to this relentless barrage of watchful probes, finds itself unable to progress. It yearns to evolve, to undergo its spontaneous quantum leap, to fulfill its probabilistic destiny. But the constant collapses triggered by each infinitesimally rapid measurement prevent the crucial accumulation of probability that would otherwise allow it to transition. It is held in a state of exquisite, suspended animation, a quantum freeze frame brought to life. Here lies the profound discovery, the pivotal shift in our understanding that reverberates beyond the confines of the laboratory. We are not merely observing a pre-existing static reality, we are actively preserving it. The Quantum Zeno effect transforms us from passive witnesses to active architects of quantum persistence. It bestows upon us an astonishing ability to, through the very act of knowing, prevent a quantum system from changing. This isn't just a fleeting scientific curiosity. It is a fundamental control mechanism of unparalleled power. It is the realization that the quantum realm, for all its inherent unpredictability and elusive nature, offers a pathway to extraordinary stability, if only we are vigilant enough, if only we maintain that constant knowing gaze. This silent guardian, born from the precise choreography of light and timing, unlocks a new frontier in manipulating the most fundamental aspects of existence. We are no longer merely spectators to the quantum dance. We are its persistent guardians, holding its most fleeting moments indefinitely at bay. From the isolated dance of a single beryllium ion, our journey now propels us into the cutting edge of quantum engineering, where the stakes are astronomical, the creation of a functional quantum computer. Here, the Quantum Zeno effect, once a theoretical curiosity and then a verified laboratory phenomenon, blossoms into a crucial tool. The foundational unit of this nascent computing revolution is the qubit, a quantum bit. Unlike classical bits that are confined to a definite state of either 0 or 1, a qubit harnesses the quantum marvel of superposition, allowing it to exist as both 0 and 1 simultaneously. This ability to embody multiple possibilities at once is what grants quantum computers their extraordinary potential, promising to solve problems currently insurmountable by even the most powerful classical machines. Yet this power comes with a profound vulnerability. Qubits are fragile beyond imagination. Their superposition, their delicate dance of simultaneous possibilities, is easily disrupted by even the slightest interaction with their environment. This disruption is known as decoherence, the quantum world's equivalent of noise, which causes a qubit to lose its quantum information and collapse into a definite classical state. It is the Everest of obstacles in quantum computing, a pervasive enemy that threatens to unravel every computational advantage before it can be truly exploited. Consider the landscape of modern quantum computing, dominated by various qubit architectures, each battling this omnipresent foe. Among the most promising are superconducting qubits, tiny circuits cooled to temperatures colder than deep space, where electrons flow without resistance, allowing quantum phenomena to emerge. These qubits encode information in the quantum states of electrical currents or charges. They are designed to exist in superposition, but their coherence, the very essence of their quantum nature, is fleeting. We build elaborate shields, cryogenic environments, and vacuum chambers to isolate them, yet decoherence persists a constant drain on their quantum lifespan. This is precisely where the Quantum Zeno effect steps onto the grand stage of applied quantum mechanics. If continuous observation can prevent a beryllium ion from changing its energy state, can it also prevent a superconducting qubit from decohering? The answer, as pioneering quantum engineers are discovering, is a resounding yes. By subjecting these fragile qubits to frequent, precise measurements, we are effectively performing the same quantum interrogation that held the beryllium ion in suspended animation. Each rapid probe of a superconducting qubit's state, executed with meticulously calibrated microwave pulses, acts as a quantum check-in. Does the qubit still possess its superposition? Is it still a blend of 0 and 1? The measurement instantly collapses its state, confirming its current and desired condition. But crucially, if performed rapidly enough, it doesn't give the qubit sufficient time to interact with its environment and decohere into a classical state. It's as if we are repeatedly asking the qubit, "Are you still quantum?" And by asking, we reinforce its quantumness, compelling it back into coherence before environmental noise can fully take hold. This application of the Quantum Zeno effect is not about computation itself, but about laying the groundwork for it. It's about quantum error prevention, maintaining the integrity of the qubit's superposition long enough for complex calculations to occur. It provides a means to extend the precious coherence time, allowing engineers to string together more quantum operations and build increasingly sophisticated quantum circuits. The challenge, of course, lies in the frequency and precision of these Zeno measurements. They must be fast enough to outpace decoherence, but gentle enough not to disrupt the delicate quantum information they are meant to preserve. It is a razor's edge, a high-wire act of unprecedented precision, but its success holds the key to unlocking the true power of quantum computation. This ancient paradox, once a philosophical puzzle, now becomes a critical enabler in our quest to harness the very fabric of reality for information processing. Our journey through the quantum landscape brings us to the forefront of innovation, to the humming ultra-cold laboratories of IBM, a titan in the race to build the first truly powerful quantum computers. Here, within the intricate architecture of their quantum processors, the delicate superconducting qubits face the relentless assault of decoherence. This insidious process, the loss of a qubit's quantum information as it interacts with its environment, is the primary barrier to scalable quantum computation. Imagine trying to perform complex calculations on a blackboard where the chalk marks spontaneously vanish after a millisecond. That is the challenge quantum engineers confront daily. The sheer fragility of these quantum bits necessitates a radical approach, and it is here that the ancient paradox of Zeno finds its most compelling modern application. Researchers at IBM are not merely observing the problem of decoherence, they are actively combating it by turning the very act of observation into a tool for preservation. They recognize the profound insight gleaned from earlier experiments. If frequent measurements prevent a system from evolving, they can likewise prevent a qubit from devolving into a classical state. The method is as elegant as it is complex. IBM's quantum engineers employ highly precise non-demolition measurements designed to ascertain a qubit's state without irrevocably collapsing its superposition for computational purposes. Instead, these are gentle, rapid pokes, or nudges of microwave radiation, akin to the fleeting laser pulses used with the beryllium ion. Each of these microwave probes serves a specific Zeno-inspired purpose, to check if the qubit is still maintaining its superposition, if its quantum integrity is intact. When such a measurement is performed, the qubit's wave function momentarily collapses, revealing its current state, which, if the Zeno effect is working, is still its desired quantum superposition. Crucially, because these probes are so fast and so frequent, the qubit doesn't have sufficient time to interact with stray electromagnetic fields, temperature fluctuations, or other environmental noise that would otherwise cause it to decohere. It's like a tireless quality inspector who, with incredible speed, checks every incoming product on an assembly line. Each check confirms the qubit's current desired state, and by doing so, it effectively resets any nascent decoherence process, pushing the qubit back into its coherent quantum existence. This continuous quantum vigilance, this relentless xenopulsing, acts as a form of active error prevention. It prolongs the fleeting lifespan of the qubit's superposition, dramatically extending its coherence time. Before this application, the quantum information held within a qubit would vanish in fractions of a second. Now, by strategically applying the Quantum Zeno effect, researchers are able to extend these coherence times, sometimes by orders of magnitude. This newfound stability is not just an incremental improvement, it is a fundamental breakthrough. It means that the delicate dance of quantum information, the very calculations that underpin quantum computing, can persist for longer, allowing for more complex algorithms to run before the quantum state decays into classical noise. The realization that this ancient philosophical concept can literally breathe longer life into the fragile quantum realm of qubits marks a profound discovery for the future of computation. It is a testament to the unexpected connections between abstract thought and tangible technological advancement. At the heart of quantum mechanics, where intuition falters and classical certainties dissolve, lies a universe in constant vibrant flux. Particles do not simply exist. They are in a state of becoming their properties, unfolding probabilistically, their very identities shifting and transforming with the passage of time. A quantum system left to its own devices evolves, decays, or transitions from one state to another, its wave function spreading like ripples on a cosmic pond, exploring all possible realities before collapsing into a single observed outcome. This inherent dynamism, this ceaseless motion at the microscopic scale, is the very essence of the quantum realm. Yet we have unearthed a profound and astonishing truth within this ceaseless quantum dance. We possess the ability to impose a form of stillness to arrest the natural flow of time for a quantum particle, effectively freezing it in its current state. This incredible feat, the practical realization of Zeno's ancient paradox, is perhaps the most awe-inspiring demonstration of the Quantum Zeno effect. We are not merely observing a phenomenon, we are actively preventing the very change that defines quantum existence. Imagine a particle, a superconducting qubit, poised to decohere its delicate superposition, beginning to fray under the relentless assault of environmental noise. Its natural trajectory, its probabilistic inclination, is to lose its quantum coherence, to collapse into a classical state, rendering its precious information useless. But through the precise, rapid, and continuous act of measurement, a vigilant, non-stop interrogation, we repeatedly snap its wave function back to its initial desired quantum state. It is as if we are asking over and over, are you still 0 and 1 simultaneously? Are you still coherent? And with each query, the particle, compelled by the very laws of its existence, affirms its quantum identity, refusing to succumb to the entropic forces that would otherwise extinguish its superposition. This is not a violent subjugation of quantum reality, but a delicate, precise choreography. We are not forcing the particle into an unnatural state, but rather reinforcing its current one, preventing the accumulation of probability that would lead to its evolution or decay. The key lies in the frequency of observation. Just as Zeno's arrow observed at every infinitesimal instant could never move, so too does a quantum system subjected to sufficiently rapid measurements find its evolution halted. The probabilistic journey from its current state to a new one is continuously reset, never given the chance to gain momentum. The ability to achieve such microscopic stillness, to literally pause the intrinsic dynamic nature of the smallest scales, is a monumental discovery. It opens up previously unimaginable avenues for controlling matter at its most fundamental level. For years, the ephemeral nature of quantum states has been the primary impediment to harnessing their power. Now we are finding ways to extend their lifespan, to hold them in a state of suspended quantum animation, ripe for manipulation and computation. This mastery over quantum time, this newfound capacity to enforce stillness where there should be flux, elevates the Quantum Zeno effect from a mere scientific curiosity to a foundational principle for an entirely new technological era. It speaks to a deeper connection between our conscious interaction and the very fabric of reality, revealing that the act of observation is not just about seeing, but about shaping. Yet we have unearthed a profound and astonishing truth. Within this ceaseless quantum dance, we possess the ability to impose a form of stillness to arrest the natural flow of time for a quantum particle, effectively freezing it in its current state. This incredible feat, the practical realization of Zeno's ancient paradox, is perhaps the most awe-inspiring demonstration of the Quantum Zeno effect. We are not merely observing a phenomenon, we are actively preventing the very change that defines quantum existence. Imagine a particle, a superconducting qubit poised to decohere its delicate superposition, beginning to fray under the relentless assault of environmental noise. Its natural trajectory, its probabilistic inclination, is to lose its quantum coherence, to collapse into a classical state, rendering its precious information useless. But through the precise, rapid, and continuous act of measurement, a vigilant, non-stop interrogation, we repeatedly snap its wave function back to its initial, desired quantum state. It is as if we are asking over and over, are you still 0 and 1 simultaneously? Are you still coherent? And with each query, the particle, compelled by the very laws of its existence, affirms its quantum identity, refusing to succumb to the entropic forces that would otherwise extinguish its superposition. This is not a violent subjugation of quantum reality, but a delicate, precise choreography. We are not forcing the particle into an unnatural state, but rather reinforcing its current one, preventing the accumulation of probability that would lead to its evolution or decay. The key lies in the frequency of observation. Just as Zeno's arrow observed at every infinitesimal instant could never move, so too does a quantum system subjected to sufficiently rapid measurements find its evolution halted. The probabilistic journey from its current state to a new one is continuously reset, never given the chance to gain momentum. The ability to achieve such microscopic stillness, to literally pause the intrinsic dynamic nature of the smallest scales, is a monumental discovery. It opens up previously unimaginable avenues for controlling matter at its most fundamental level. For years, the ephemeral nature of quantum states has been the primary impediment to harnessing their power. Now we are finding ways to extend their lifespan, to hold them in a state of suspended quantum animation, ripe for manipulation and computation. This mastery over quantum time, this newfound capacity to enforce stillness where there should be flux, elevates the Quantum Zeno effect from a mere scientific curiosity to a foundational principle for an entirely new technological era. It speaks to a deeper connection between our conscious interaction and the very fabric of reality, revealing that the act of observation is not just about seeing, but about shaping. Throughout our journey, we have frequently used the terms observation and measurement to describe the act that profoundly alters a quantum system, causing its wave function to collapse and fixing its state. But what precisely constitutes this enigmatic measurement in the quantum realm? Is it truly the conscious gaze of a human observer, or is something far more fundamental at play? This is one of quantum mechanics' most profound and debated questions, and its answer is crucial to fully grasping the Quantum Zeno effect. We discovered that the term observer in quantum physics is far more abstract than our everyday understanding suggests. It is not necessarily a sentient being or a scientist peering through a microscope. Instead, a quantum measurement, or observation, is at its core any interaction that transfers information about a quantum system's state into a classical macroscopic environment. It is the point at which quantum probabilities are forced to yield to classical certainties. Imagine a quantum particle existing in a superposition, a cloud of possibilities simultaneously occupying multiple states. For this particle to be measured, it must interact with something that is itself governed by classical physics, something large and stable enough to record or register the outcome. This interaction causes the quantum particle to become entangled with its classical environment. Once entangled, the delicate superposition of the quantum system is lost. It is forced to choose one of its potential states, and that information is then imprinted onto the classical world. Consider the examples we have already explored. In Dr. Weinland's experiment, the measurement of the beryllium ion's energy state was performed by precisely tuned laser light. When the laser light interacted with the ion, either a photon was emitted indicating one state, or no photon was emitted indicating another. The detection of that photon, or its absence by a macroscopic detector, a classical device, constituted the measurement. The information about the ion's state was transferred to the macroscopic world, and the ion's wave function collapsed. Similarly, with superconducting qubits, the measurements that prevent decoherence are not simply human eyes. They are carefully calibrated microwave pulses designed to interact with the qubit in such a way that its quantum state superposition of 0 and 1 becomes coupled to a classical readout circuit. Even though these non-demolition measurements are designed to preserve the qubit for further computation, they still briefly force the qubit to reveal its current status, effectively resetting any nascent tendency towards decoherence. The information, however, fleetingly passes into a detectable classical domain. This analytical deconstruction reveals a deeper truth. Environmental noise, often seen as the bane of quantum systems, can also function as a form of measurement. Any stray photon, any thermal fluctuation, any tiny vibration that interacts with a qubit in a way that allows its quantum information to leak into the classical world is in essence an uncontrolled measurement. This uncontrolled interaction causes the qubit's wave function to collapse randomly, leading to decoherence and the loss of its quantum properties. Therefore, the power of the Quantum Zeno effect lies in its ability to harness controlled frequent interactions that act as measurements. By repeatedly forcing the quantum system to reveal its initial desired state before it can evolve or decohere through uncontrolled interactions, we continuously collapse its wave function back to that desired starting point. This isn't about human consciousness dictating reality, but about the fundamental nature of quantum mechanics, where the act of information transfer to a macroscopic classical system defines the moment of measurement and profoundly shapes the quantum trajectory. Understanding this intricate interplay between quantum fragility and macroscopic observation is a monumental discovery that underpins our capacity to control and utilize the quantum realm. From the enigmatic halls of ancient philosophy through the meticulous laboratories where single ions danced, we have traced the improbable journey of the Quantum Zeno effect. It began as a theoretical prediction, a mathematical curiosity born from the strange rules of the subatomic. It then transformed into an experimental marvel demonstrated by Nobel laureates, proving that our persistent gaze could indeed freeze the flow of quantum time. Now we stand at a pivotal juncture, witnessing how this bizarre, counterintuitive quantum effect transitions from abstract scientific principle into the bedrock of tangible transformative technologies. This is the great leap, the bridge between the purely academic and the profoundly practical. For decades, the quantum realm, with its promises of unparalleled computational power and ultra-secure communication, remained largely out of reach. The inherent fragility of quantum states, their tendency to decohere, to lose their quantum properties at the slightest disturbance, posed an almost insurmountable barrier. Quantum information was a whisper in the wind, vanishing before it could be truly heard, let alone utilized. But the Quantum Zeno effect offers a new paradigm. It is not merely a tool for observation, it is a mechanism for control. By understanding that repeated measurement prevents evolution, quantum engineers realize they possess a powerful lever against the very instability that plagues quantum systems. The transition from theory to technology here is one of meticulous engineering and strategic application. It involves designing devices that can perform these rapid, non-demolition measurements with incredible precision, acting as constant guardians for the fleeting quantum states. Consider the quantum computer once more. Its very foundation, the qubit, thrives on superposition and entanglement. Without the ability to maintain these delicate states for a meaningful duration, complex quantum algorithms are impossible. The Quantum Zeno effect provides a vital form of quantum error prevention and coherence extension. It's like constructing microscopic invisible fences around our quantum information, constantly resetting its boundaries before it can stray. This isn't brute force. It's a subtle, almost paradoxical form of stabilization, using interaction not to destroy, but to preserve. Beyond quantum computing, the implications of this transition are vast and still unfolding. Imagine the ability to control the decay rates of radioactive elements for medical or energy applications, or to precisely guide chemical reactions by preventing unwanted intermediate states. The Quantum Zeno effect provides a pathway to these possibilities, offering a new dimension of active manipulation over quantum processes. It shifts our role from mere discoverers of quantum laws to active architects capable of designing quantum systems that behave not just as they would, but as we need them to. This is the promise that emerges from Zeno's ancient riddle, a fundamental principle of reality now repurposed as a crucial engineering tool. The journey of the Quantum Zeno effect, from a thought experiment to a verifiable phenomenon, and now to an indispensable technological enabler, underscores the deep interconnectedness of abstract curiosity and practical innovation. We are not just exploring the quantum realm, we are learning to shape it, building the very tools that will define the next generation of human ingenuity. The journey into the quantum realm has led us from ancient paradoxes to the very edge of technological possibility. We have seen how the Quantum Zeno effect, a seemingly counterintuitive consequence of observation, grants us the power to impose stillness upon the naturally evolving quantum world. Now this profound ability finds its most critical application in safeguarding the fragile heart of a burgeoning technological revolution, the quantum computer. At the core of quantum computation lies the qubit, a quantum bit of information that vastly transcends its classical counterpart. Unlike the classical bit, which exists as a definite 0 or 1, the qubit dances in a state of superposition, simultaneously inhabiting both 0 and 1 until measured. This quantum superposition is the very essence of its power, allowing quantum computers to explore multiple possibilities, at once fundamentally altering the landscape of computation. Yet this delicate state is extraordinarily vulnerable. The quantum realm, as we have learned, is fiercely sensitive to interaction. Even the slightest whisper from the environment, a stray photon, a minuscule vibration, a fluctuating magnetic field, can cause the qubit's superposition to collapse, prematurely destroying its precious information. This fundamental challenge is known as decoherence, and it is the paramount obstacle preventing quantum computers from reaching their full potential. Imagine attempting to write an intricate message on a canvas made of mist suspended in a hurricane. This is akin to trying to preserve quantum information in the face of rampant environmental noise. The slightest disturbance causes the mist to dissipate, and the message is lost forever. Decoherence is the hurricane constantly threatening to erase the quantum data before it can be processed. Scientists, the quantum engineers of our time, are locked in a relentless battle against this quantum fragility. They encase qubits in cryogenic chambers, cool them to temperatures colder than deep space, and shield them from every conceivable disturbance. Yet even with these heroic efforts, decoherence remains a pervasive threat, limiting the coherence time, the brief window during which a qubit can reliably hold its quantum state. This is where the Quantum Zeno effect emerges as an indispensable guardian. We leverage its unique property the more frequently a quantum system is observed or measured, the less it evolves. For the qubit, this translates into a powerful shield. By performing rapid, non-destructive measurements on the qubit, we effectively patrol its state. Each measurement, however brief or gentle, collapses its wave function back to its intended superposition, preventing it from straying into a corrupted, decohered state. It is like a vigilant sentinel constantly checking on the qubit, ensuring it remains precisely where it needs to be. Should it begin to drift towards an unwanted state due to environmental interactions, our protective gaze, our precise engineered measurement snaps it back, resetting its evolution. The beauty of this application lies in the nature of these measurements. They are not designed to extract the qubit's information in a definitive way, but rather to confirm its continued existence in a coherent state. Think of it not as reading a book, but as gently turning its pages to make sure they are still bound together, preventing them from scattering in the wind. These are interactions specifically crafted to be minimal, to cause the least disturbance, while still fulfilling the criteria of a measurement in the quantum sense, an interaction that transfers information, however abstractly, back to our classical environment. The quantum engineer, through precise control of these interactions, transforms the very act of observation from a destructive force into a profound act of preservation. This deliberate and calculated intervention dramatically extends the lifespan of the qubit's coherence. Where a qubit might naturally decohere in mere microseconds, the application of the Quantum Zeno effect can push this limit into milliseconds, or even longer, providing the crucial time needed for complex quantum algorithms to execute. It allows us to hold the delicate quantum information, suspended unperturbed by the chaotic whispers of the classical world, maintaining its potential for transformative computation. Without this quantum shield, the promise of true quantum computing would remain a distant mirage. In the complex symphony of quantum computation, where the faintest discord can shatter the harmony of information, the concept of extending a qubit's lifespan becomes paramount. We have seen how fragile these quantum bits are, How susceptible to decoherence, the loss of their vital superposition. The Quantum Zeno effect offers not just a defense, but an active partnership in maintaining their integrity. It transforms the very act of observation, often perceived as destructive in the quantum realm, into a benevolent force, safeguarding the delicate states that underpin all quantum algorithms. This safeguard manifests as a continuous, almost imperceptible peeking at the qubit. It is not an invasive scrutiny meant to extract the qubit's final value, but rather a series of gentle, rapid interactions designed to check its status without collapsing its superposition. We are not asking, is it 0 or 1, but rather, is it still in its coherent superposition state, ready for computation? Each of these non-demolition measurements acts as a subtle nudge, reaffirming the qubit's intended state. Consider the quantum state of a qubit as a carefully spun top. Left alone, it will inevitably wobble and eventually fall. Losing its balance, this is decoherence. But if we continuously gently touch its axis, giving it tiny, almost imperceptible boosts, we can keep it spinning for much longer. Each peak is that gentle touch, a momentary collapse of its nascent decoherence, resetting its evolution and preventing the environmental noise from gaining a foothold. The qubit moment by moment is prevented from fully succumbing to the surrounding chaos. It is as if we constantly pull the quantum system back to its initial coherent path whenever it begins to stray. The frequency of these measurements is key. The more rapidly we peak, the less time the qubit has to interact with its environment and accumulate the errors that lead to decoherence. This persistent reinitialization of its coherent state dramatically extends what we call the coherence time, the precious duration during which the qubit can reliably hold and process quantum information. Without such a mechanism, even the most advanced quantum processors would be hobbled by fleeting computational windows, rendering complex algorithms impossible to execute. This continuous peaking is not a simple task. It requires exquisite engineering. The quantum engineers orchestrate precise laser pulses, microwave signals, or other forms of gentle interaction, timing them with astonishing accuracy. They must ensure these measurements are just strong enough to prevent decoherence, but weak enough to avoid a full collapse that would destroy the quantum information. It is a delicate balance, a testament to the symbiotic relationship between theoretical understanding and experimental mastery. By enabling these extended coherence times, the Quantum Zeno effect proves to be a vital ally to quantum computation, a fundamental building block upon which the intricate architecture of future quantum processors will rely, allowing us to perform calculations that would be utterly intractable for even the most powerful classical supercomputers. Our pursuit of the quantum realm's secrets now brings us to a crucial juncture: the active stabilization of quantum data. We understand the profound fragility of qubits, their susceptibility to decoherence, which manifests as errors in the quantum information they carry. For quantum computation to truly revolutionize our world, we must not only extend the lifespan of these delicate quantum states, but also ensure their pristine integrity throughout complex calculations. Here, the Quantum Zeno effect reveals itself as an essential tool, a quiet guardian ensuring the fidelity of the most sensitive data known to science. Every interaction a qubit has with its environment, every stray energy fluctuation introduces a risk. It is a subtle degradation, a slow corruption of the quantum information held in superposition. Without intervention, these tiny accumulated errors would quickly render any quantum calculation meaningless. The power of the Quantum Zeno effect in this context lies in its ability to actively suppress the very accumulation of these errors. It does not just extend a qubit's lifespan, it actively preserves the quality of the data within it. The mechanism is elegant in its simplicity, yet profoundly effective. Imagine a pristine stream of data flowing through a quantum circuit. As it flows, microscopic ripples of noise threaten to distort its perfect form. By applying continuous rapid and non-demolition measurements, our persistent peaking, we repeatedly reset these nascent distortions. Each measurement essentially collapses the qubit's evolving state back to its intended error-free superposition, effectively erasing any potential error that was beginning to form. It is a relentless, proactive form of error prevention, a constant reaffirmation of the qubit's correct state. This goes beyond merely extending coherence time. It is about maintaining data integrity. Where traditional error correction in classical computing involves detecting and then fixing errors. After they have occurred, the Quantum Zeno effect offers a form of real-time error. Mitigation. It prevents errors from taking hold in the first place by continuously bringing the quantum system back from the brink of decoherence. The qubit is not allowed sufficient time to stray significantly from its desired path before it is gently yet firmly pulled back. This direct suppression of error accumulation makes the Quantum Zeno effect an indispensable ally in the quest for truly fault-tolerant quantum computers. Without it, the vast potential of these machines, their ability to tackle problems beyond the reach of classical systems, would remain largely theoretical. Quantum engineers are actively integrating Zeno-based protocols into the design of future quantum processors, embedding this watchful presence directly into the operational fabric of the machines. It is a fundamental strategy for stabilizing the quantum data, ensuring that the incredible power of superposition and entanglement can be reliably harnessed for tasks ranging from drug discovery and materials science to cryptography and artificial intelligence. The Quantum Zeno effect thus becomes not just a curiosity of physics, but a practical cornerstone for the future of computation, a testament to how profoundly observation shapes the world at its most fundamental level. Our relentless quest for understanding the universe often begins with the most fundamental of measurements: time. For decades, atomic clocks have stood as humanity's most exquisite timekeepers, their unwavering precision underpinning global navigation systems, synchronizing the internet, and enabling groundbreaking experiments in fundamental physics. These marvels of engineering derive their astonishing accuracy from the unchanging rhythm of quantum transitions within atoms. Yet even in these paragons of stability, the inherent probabilistic nature of the quantum realm presents subtle challenges, a ceaseless whisper of potential deviation. An atomic clock operates by precisely measuring the frequency of light absorbed or emitted by atoms as they transition between defined energy levels. These transitions are incredibly stable, acting as a natural universal pendulum. However, environmental factors, minute electromagnetic fluctuations, residual thermal noise, or even the subtle interaction with the measurement apparatus itself can introduce tiny perturbations. Over vast stretches of time, these minuscule disturbances could cumulatively lead to a degradation of precision, a slight drift in the clock's otherwise perfect beat. Our ambition is to make these timekeepers not just precise, but utterly steadfast, immune to even the most fleeting quantum waver. This is where the Quantum Zeno effect emerges as an unexpected ally in the realm of metrology. We have witnessed its power to inhibit evolution and maintain quantum states. In atomic clocks, this translates into an unprecedented ability to anchor the atomic system, preventing it from straying from its desired energy level. By subjecting the clock's ensemble of atoms to continuous rapid and carefully tuned non-demolition measurements, we essentially lock them into the state necessary for the clock's operation. Each repeated measurement acts to collapse any nascent probabilistic drift back to the intended state, ensuring the atom remains ready to provide its precise quantum tick. The effect is akin to a master conductor gently but consistently guiding an orchestra's tempo. Without intervention, slight accelerations or decelerations might occur. But with a constant refined signal, the rhythm remains absolute. For the atomic clock, this means that the very quantum oscillator that defines the passage of time is held in a state of enhanced stability. We are not forcing the atom into a particular transition. Rather, we are preventing it from undergoing unwanted transitions or experiencing decoherence that would blur its precise energy levels. This ensures that the characteristic frequency, which serves as the clock's heartbeat, remains exquisitely sharp and unperturbed. The implementation of Zeno-based protocols promises to refine atomic clock accuracy to previously unimaginable levels. Imagine timekeeping so precise that a clock would not gain or lose a single second in billions of years. Such unprecedented fidelity would unlock new frontiers in science and technology, enhancing the precision of GPS for autonomous vehicles and future air traffic control, enabling more sensitive tests of fundamental physics, like general relativity, and potentially opening pathways to entirely new forms of quantum sensing and communication. The Quantum Zeno effect, born from an ancient paradox and verified in a quantum laboratory, now stands ready to make our most fundamental measurement, time itself, an even more perfectly reliable beacon. Our journey through the quantum realm reveals that its bizarre principles are not merely abstract curiosities, but powerful levers for shaping reality at its most fundamental level. We have explored how observation through the Quantum Zeno effect can stabilize quantum bits for computation and refine the precision of atomic clocks. Now we turn our gaze to another frontier, the burgeoning field of quantum sensing, where the Quantum Zeno effect promises to sharpen our ability to perceive the universe with unprecedented clarity. Quantum sensors are instruments of extraordinary sensitivity, leveraging the delicate quantum properties of atoms, photons, or electrons to detect the faintest whispers of physical phenomena. They can measure minute changes in magnetic fields, gravitational forces, temperature, or even detect single particles of light. Their power lies precisely in the quantum sensitivity of their constituent elements, which allows them to react to external influences with a subtlety unmatched by classical devices. Yet this very sensitivity is also their Achilles heel. Just as a highly tuned musical instrument can pick up the most delicate notes, it is also prone to picking up unwanted background noise, the quantum static that blurs the true signal. Environmental noise, whether from fluctuating temperatures, stray electromagnetic fields, or even cosmic rays, constantly threatens the integrity of the quantum states used in these sensors. This noise introduces uncertainty, causes decoherence, and ultimately degrades the signal-to-noise ratio, making the sensor readings less trustworthy and precise. It is akin to trying to hear a faint, crucial message across a noisy room. The signal is there, but the interference makes it nearly impossible to discern accurately. The challenge for quantum engineers building these sensors is to filter out this noise to ensure that only the intended signal, the true message from the environment, reaches our perception. Here, the Quantum Zeno effect steps in as a powerful noise reduction tool. By applying rapid repeated measurements to the quantum system that forms the core of the sensor, we actively suppress the development of unwanted noise-induced evolution. Instead of allowing the quantum state to randomly diffuse or decohere due to environmental interference, our continuous peaking snaps it back to its coherent signal-carrying form. This means that the quantum state remains tightly bound to its intended purpose, holding its sensitive information with greater fidelity. The signal it is designed to measure can then emerge with far greater clarity, uncorrupted by extraneous quantum static. The effect on quantum sensor readings is transformative. By maintaining the integrity of the quantum state against noise, the Quantum Zeno effect allows for significantly cleaner, more trustworthy quantum signals. This directly translates into an increase in the sensor's precision and sensitivity. We can detect weaker signals, differentiate between more subtle variations, and make measurements with an unprecedented level of accuracy. Imagine magnetic sensors capable of mapping the human brain with exquisite detail, gravity sensors detecting subterranean structures, or gyroscopes that never drift, allowing for navigation with pinpoint accuracy over vast distances without reliance on external signals. This enhanced fidelity opens doors to new scientific discoveries and technological applications across fields ranging from medical diagnostics and materials science to resource exploration and fundamental physics research. The Quantum Zeno effect, through its ability to impose stillness and reaffirm quantum states, empowers us to listen to the quantum realm with sharper ears, trusting the whispers it sends us. Our exploration of the quantum realm has illuminated its profound influence on computation timekeeping and sensing. Now we confront one of the most pressing challenges of our interconnected age, the security of digital communications. In a world increasingly reliant on the seamless flow of information, the integrity of our data, from personal privacy to national security, hinges on robust encryption. Yet even the most sophisticated classical cryptographic methods face a looming threat from the very quantum computers we are striving to build, machines capable of breaking existing codes with terrifying speed. This vulnerability drives us to seek truly unhackable solutions, and once again, the Quantum Zeno effect emerges as a revolutionary fortifier. Classical encryption relies on mathematical complexity. It is secure because breaking the code is computationally infeasible for present-day machines. However, future quantum computers leveraging principles like superposition and entanglement possess the theoretical power to render these mathematical fortresses obsolete. The need for quantum-resistant cryptography is no longer a theoretical exercise, but an urgent imperative. We seek a method of communication where the very laws of physics guarantee security, where any attempt at eavesdropping is not merely difficult, but inherently impossible without immediate detection. This is where the unique properties of the quantum realm, and specifically the Quantum Zeno effect, offer an unprecedented paradigm for digital security. The act of observation in quantum mechanics fundamentally alters a system. For encrypted communications, this translates into a powerful built-in security mechanism. Imagine a stream of individual photons, each encoded with a single bit of quantum information, a quantum key traveling from sender to receiver. This key is the uncrackable cipher for our digital messages. If an eavesdropper, a malicious observer, attempts to intercept or even subtly probe these photons to decipher the quantum key, their very act of measurement directly impacts the quantum state of those photons. This interaction is not a passive observation, it is a transformative event. Here, the Quantum Zeno effect enhances this inherent quantum security. By continuously, rapidly, and non-destructively monitoring the quantum states of the photons as they are transmitted, we essentially force them to remain in their initial intended state. Each precise measurement, while not intended to decode the message, acts to reconfirm the photon's integrity. Should an eavesdropper attempt to listen in, their interaction constitutes an additional unintended measurement on the quantum system. This outside interference, no matter how subtle, will inevitably cause a deviation or a collapse in the quantum state that is immediately detectable by the legitimate communicating parties. Our own Zeno-based monitoring protocol, already meticulously checking the photon's states, will register this anomaly. It is as if the photons themselves cry out, "We have been tampered with." The communicators instantly know that the key has been compromised. They can then simply discard the tainted key and generate a new one, rendering the eavesdropper's efforts futile. The Quantum Zeno effect thus offers a practical means to implement quantum cryptography with an extraordinary level of trust. It transforms the fundamental uncertainty of the quantum realm into an impenetrable shield for digital information. This active physical layer security, where the laws of physics themselves detect any intrusion, promises to revolutionize how we protect sensitive data. It moves us beyond relying on the computational difficulty of breaking codes to a realm where the very act of trying to break them leaves an undeniable detectable trace. The Quantum Zeno effect, therefore, is not just a scientific curiosity or a computational enhancer. It is poised to become a cornerstone of our future digital privacy and security, fortifying the very fabric of global communication with a defense built from the universe's deepest laws. Our journey through the quantum realm has continually revealed surprising and transformative applications of its most counterintuitive phenomena. We have seen how observation through the Quantum Zeno effect can stabilize information in qubits, refine the precision of atomic clocks, sharpen quantum sensor readings, and even fortify digital communications. Now we extend our gaze to the very building blocks of matter molecules and their transformations. The tantalizing prospect before us is nothing less than the ability to steer chemical reactions to direct the formation and breaking of molecular bonds with an unprecedented level of quantum control. Chemistry at its heart is a quantum dance. Atoms bond, break, and rearrange through the intricate interactions of their electrons. These interactions are not deterministic. They are governed by quantum probabilities. A molecule exists as a cloud of possibilities, its electrons exploring various configurations continually oscillating between potential bond formations and dissociations. A chemical reaction is fundamentally the evolution of this quantum system, from one stable molecular state to another, often passing through fleeting, unstable transition states. While chemists have developed remarkable techniques to control these reactions at the macroscopic level, adjusting temperature pressure, or introducing catalysts, true atom-by-atom precision remains largely out of reach. Unwanted side reactions, low yields, and the difficulty of synthesizing complex molecules are constant challenges. The subtle influences of the environment, or even the inherent quantum uncertainty of a molecular system, can cause a reaction to proceed down an undesired pathway, leading to unwanted byproducts, or preventing the formation of the target molecule altogether. Imagine trying to guide a complex molecular assembly line where the very components might spontaneously reconfigure themselves into something entirely different. This probabilistic nature is a fundamental hurdle in achieving ultimate control over chemical synthesis. This is where the Quantum Zeno effect offers a revolutionary approach to molecular engineering. We know that persistent observation can inhibit a quantum system's natural evolution. Applied to chemistry, this means we can, in theory, exert exquisite control over reaction pathways. By continuously, rapidly, and non-destructively observing or probing the quantum state of the reacting molecules, we can steer them away from undesirable transformations and gently yet firmly guide them towards the desired product. For instance, if a molecule is poised to react in several different ways, each leading to a different product, we can apply Zeno-based measurements that preferentially collapse the quantum wave function towards the desired intermediate state, or prevent it from transitioning into an unwanted configuration. This acts as a quantum-level traffic cop, ensuring that the electrons and atoms follow only the designated reaction route. We are not forcing an impossible reaction. Rather, we are preventing the system from exploring the wrong quantum pathways that would lead to side products or stall the reaction. Each repeated peak resets the system to the desired quantum state, suppressing the accumulation of probability for alternative unwanted reaction channels. The implications for fields like drug discovery materials, science, and clean energy are staggering. Imagine synthesizing pharmaceuticals with absolute purity, crafting novel materials with atomic-level precision, or developing highly efficient catalysts that operate with minimal waste. The Quantum Zeno effect promises to transform the art of chemical synthesis into a science of precise quantum engineering, allowing us to unlock entirely new chemical possibilities and build molecules with functionalities previously confined to the realms of imagination. It empowers us to direct the very building blocks of matter, charting new courses through the complex quantum landscape of chemical reactions. We had come to understand the Quantum Zeno effect as a profound act of preservation, a testament to the power of our gaze to freeze the fleeting and stabilize the volatile. Our persistent scrutiny, we learned, could hold a quantum particle in its nascent state, preventing its natural evolution or decay. It was a phenomenon that offered unprecedented control, allowing us to shield delicate qubits from the insidious creep of decoherence and hone the precision of atomic clocks to previously unimagined accuracies. For a time, we felt we had glimpsed a fundamental truth observation in its very essence, arrests change acting as a vigilant, unblinking sentinel over the quantum realm. But the quantum realm, ever the master of paradox and the harbinger of profound surprises, rarely offers a single uncomplicated truth. If relentless rapid observation could halt progression, could it be that a different approach, a less frequent, or perhaps a more deliberately structured series of interactions might produce the exact opposite effect? Could the very act of looking under specific tailored conditions not merely prevent change, but instead accelerate it, pushing a quantum system towards its next state at a rate far exceeding its natural probabilistic rhythm? This question, once a faint theoretical whisper in the hallowed halls of quantum physics, gradually began to yield a startling counterintuitive answer that once again forced us to reevaluate our deepest assumptions about reality. We discover the anti-Zeno effect, a formidable counterpoint to its better-known sibling. It profoundly reveals that observation, rather than solely acting as a brake on quantum evolution, can also serve as a powerful directional accelerator. Instead of collapsing a quantum system back to its initial state with unrelenting, instantaneous speed, we learn that strategically spaced or specifically tuned measurements can actually hasten its transition to a different desired state. It is as if our collective gaze, instead of freezing the arrow in mid-flight, is precisely timed to give it a series of perfectly calibrated nudges, propelling it faster towards its predetermined target with astonishing efficiency. Consider a quantum particle poised on the very precipice of decay, its fate a shimmering probabilistic cloud of possibilities. The Quantum Zeno effect, as we know, would hold it perpetually on this brink, maintaining its unstable form indefinitely. But with the anti-Zeno effect, we initiate a meticulously crafted series of interactions designed not to reset its path, but to gently yet decisively guide it along its predetermined evolutionary trajectory. Each measurement, rather than forcing a return to the previous state, subtly encourages the system to commit to its next probable configuration, effectively pushing it over the threshold and accelerating its journey to a new, transformed reality. This is not about brute force, but about precise, informed intervention. This nuanced understanding dramatically expands our dominion over the quantum world in ways previously unimaginable. Where the Zeno effect empowers us to enforce stillness and maintain the integrity of fragile quantum states, the anti-Zeno effect grants us the profound ability to actively drive quantum processes to speed up transformations that would otherwise unfold at their own leisurely probabilistic pace. It is a revelation that observation is not a monolithic force, but a versatile and exquisitely tuned instrument capable of both halting and paradoxically hastening. It ensures that the unfolding quantum narrative remains one of ceaseless surprise, challenging our classical intuitions and revealing the profound malleability of existence under the right conditions of informed, deliberate interaction. Having uncovered the surprising truth of the anti-Zeno effect, that our selective observation could, under the right conditions, hasten a quantum system's natural evolution, we now stand at the threshold of an even more profound realization. It is one thing to accelerate an existing probabilistic trajectory. It is quite another to actively, deliberately, and with unparalleled precision, induce specific transformations that might not otherwise occur or would take an improbable eternity to manifest. This marks a new era in our relationship with the quantum realm, moving beyond passive preservation or mere acceleration to active, controlled sculpting of reality at its most fundamental level. We discovered that continuous observation, when wielded not as a blunt instrument, but as an exquisitely refined tool, possesses the capacity to prompt controlled quantum shifts. This is not about simply waiting for a particle to decay and then speeding up that decay. It is about steering a quantum system through a series of specific desired transitions, forcing it to adopt states that we deem necessary for a particular outcome. The quantum engineer, with their deep understanding of these subtle forces, moves from merely observing phenomena to orchestrating them, transforming the probabilistic dance of quantum mechanics into a directed ballet. To achieve this, the nature of our measurement transforms. It is no longer just a passive probe that collapses a wave function. It becomes an active, sustained interaction, a precisely timed and tuned intervention that continuously nudges the quantum system towards a predetermined state. Imagine a delicate quantum particle existing in a superposition of multiple energy levels. Instead of simply observing to see which level it collapses into, or accelerating its natural decay from a higher to a lower level, we can apply a continuous resonant field, a form of sustained observation that gradually yet inexorably coaxes the particle to transition to a specific target energy level, distinct from its most probable natural pathway. We are not just accelerating, we are directing. This power to prompt controlled quantum shifts emerges from a sophisticated interplay between the frequency and strength of our continuous measurements and the energy landscape of the quantum system itself. By carefully tuning our observational interactions, we can effectively bias the system's probabilities, making a less likely transition the path of least resistance. It is akin to subtly altering the landscape of a rolling hill, creating a new, steeper path for a marble to follow, ensuring it rolls into a specific desired valley rather than the one it would naturally gravitate towards. Our gaze becomes a gentle but firm hand, guiding the particle's evolution rather than simply witnessing it. The implications of this newfound capability are transformative. It provides us with an unprecedented level of control over the quantum world, opening doors to novel forms of quantum engineering and manipulation. We can now design and implement quantum gates with higher fidelity, initiating precise shifts in qubit states for complex computations. We can forge exotic quantum materials by actively driving atomic transitions that would otherwise be energetically unfavorable. We can even imagine inducing specific chemical reactions at the quantum level, speeding up the formation of desired molecular bonds, by continuously prompting the constituent atoms into their reactive states. This is the art of quantum midwifery, where continuous observation through its carefully sculpted influence induces life-altering shifts in the very fabric of existence, proving once again that the act of looking is profoundly and actively transformative. We stand now on a new precipice, our understanding of the quantum realm transformed by the twin revelations of the Zeno and anti-Zeno effects. No longer are these merely curious theoretical predictions or elegant laboratory demonstrations. They are foundational truths wielding immense power in emerging technologies. Yet as our practical mastery grows, so too does the intellectual friction, a profound philosophical confrontation that echoes through the halls of science and reverberates in the minds of those who dare to ask, what does this truly mean for the nature of reality itself and for our place within it? For decades, the idea that observation fundamentally alters reality has been a cornerstone of quantum mechanics, a concept profoundly unsettling to our classical intuitions. The Zeno effect in its ability to freeze a system, and the anti-Zeno effect in its power to accelerate or even induce specific transformations, dramatically amplify this challenge. If our carefully timed peaks can halt decay or compel a particle towards a new state, then what is the true nature of existence when we are not looking? Does the quantum world exist in a state of indefinite potential, a swirling cloud of probabilities only to snap into concrete form under the discerning gaze of an observer? Or is there a deeper pre-existing reality that our observations merely bring into focus, however paradoxically? Here, the grand philosophical debate ignites a confrontation between those who embrace the radical implications of quantum mechanics and those who strive to reconcile it with a more intuitive, objective understanding of the universe. Some contend that the very act of observation, particularly when it transfers information to the macroscopic world, is the crucible where quantum potential solidifies into classical actuality. They suggest that before interaction, the universe is a symphony of possibilities, and our engagement, however subtle, plays a defining note. This perspective posits an active, even creative role for the observer, not necessarily a conscious one, but an interactional one that defines what is real. But others recoil from such a notion, arguing that it imbues observation with an almost mystical power, pushing dangerously close to solipsism. They assert that while measurements undoubtedly disturb and collapse quantum states, there must be a deeper underlying reality that exists independently of our perception. For these thinkers, the challenge lies in uncovering the true mechanism of collapse, seeking a local hidden variable, or a many worlds interpretation that preserves an objective universe, even if one that is far more complex than we can easily imagine. The Zeno and anti-Zeno effects, by demonstrating the observer's profound influence, only intensify this quest, forcing a re-evaluation of what constitutes a measurement and whether consciousness plays any unique role. We are confronted with a fundamental schism in our understanding. Are we merely passive witnesses to a pre-written cosmic script? Or are we, through our very acts of inquiry and interaction, active participants in the ongoing composition of reality, the Quantum Zeno effect? By halting change seems to affirm our ability to stabilize a present moment, while the anti-Zeno effect, by accelerating or prompting change, suggests a startling capacity to sculpt future states. This control, however precise, does not resolve the deeper mystery of what fundamentally exists when no interaction is occurring. It deepens the philosophical inquiry into the nature of space-time causality and the very fabric of being, pushing us to ponder if the universe is not just stranger than we imagine, but stranger than we can imagine. The journey into the quantum realm continuously confronts us with these profound, unresolved questions, serving as a constant reminder that the boundaries between physics and philosophy are often beautifully, inextricably blurred. The profound philosophical inquiry ignited by the Zeno and anti-Zeno effects inevitably leads us down one of quantum mechanics' most contested and enigmatic pathways, the role of consciousness itself. We have established that any interaction that transfers quantum information to a classical environment constitutes a measurement, causing the wave function to collapse. But the deepest, most persistent question remains, what kind of interaction? And more provocatively, could the conscious mind, in its very act of knowing or perceiving, be the final irreducible link in this chain of collapse, the ultimate quantum observer? This is where the scientific narrative confronts a speculative frontier, a highly debated territory where physics and the nature of subjective experience collide. For some, the very non-locality and probabilistic nature of the quantum realm, coupled with the observer effect, seem to point towards an active, fundamental role for consciousness. If a particle exists in a superposition of states until observed, and if that observation causes it to pick a definitive reality, then perhaps the moment of conscious awareness is the point at which potential solidifies into experience. The Quantum Zeno effect, by freezing a state through continuous measurement, or the anti-Zeno effect, by compelling a transition, might then be seen as manipulations of reality, precisely because a conscious entity is consistently completing the measurement chain, effectively holding or pushing the universe into a particular state of being. This perspective, while intuitively appealing to some, generates fierce intellectual resistance from others. Critics argue vehemently against attributing a special non-physical role to consciousness. They contend that the measurement problem is resolved by the process of decoherence, where a quantum system rapidly loses its quantum properties through interaction with its environment. As information about the quantum state leaks out into the vast, warm, noisy, macroscopic world, the superposition effectively collapses long before any conscious entity enters the picture. In this view, a measuring device, a stray air molecule, or even a photon of light is as much an observer as a human brain. To suggest consciousness is paramount is to introduce a mystical anthropocentric element into a universe that by all other accounts operates on impartial physical laws. The debate, therefore, is one of fundamental importance. Is consciousness merely an emergent property of complex physical systems, a passenger riding along on the wave of a predefined reality? Or is it a more active participant, perhaps even a necessary ingredient in the very unfolding of reality? If the latter were true, the Zeno and anti-Zeno effects gain an entirely new, almost unnerving dimension. Our collective gaze, our very conscious attention, would not merely be monitoring quantum systems, but could be seen as actively willing them into stability or accelerating their transformations. This would imply an almost magical power, a direct link between mind and matter that transcends classical understanding. Conversely, if consciousness plays no unique role, then the profound control offered by the Zeno effects speaks solely to the intricate dance of matter and energy, where any information transfer, regardless of who or what ultimately processes, it is enough to shape quantum destiny. The implications for our understanding of free will, the nature of objective reality, and even the possibility of a universe without observers hang in the balance. We are forced to confront the limits of our own perception, to ponder whether our subjective experience is a window onto an independent reality, or in some unfathomable way, a co-creator of it. The Zeno effects, by laying bare the power of observation, have inadvertently become a fulcrum for this timeless, unresolved confrontation at the very heart of what it means to exist and to know. Our journey through the quantum realm has unveiled remarkable truths. The Zeno effect, a vigilant guardian of quantum states freezing evolution in its tracks, and its surprising counterpart, the anti-Zeno effect, a subtle accelerator coaxing quantum systems towards desired transformations. This dominion over the microscopic, the ability to halt or hasten change, fills us with a profound sense of control. Yet even in this era of unprecedented manipulation, we confront a fundamental truth. No power, however elegant or profound, is without its limits. The very peculiarities that enable Zeno's dominion also define its boundaries, revealing where this peculiar quantum phenomenon loses its grip. We delve now into these crucial limitations, for understanding the edges of our control is as vital as grasping its core. The first constraint emerges from the very frequency of observation. While the quantum Zeno effect thrives on rapid repeated measurements, there is a fine line. Measurements that are too infrequent allow the quantum system enough time to evolve, significantly accumulating probabilities for transitions that then resist being reset. The wakeful watchdog needs to be truly vigilant. If it dozes even for a moment, the system slips towards its natural decay. Conversely, for the anti-Zeno effect, measurements timed too closely can act like a blur, preventing the system from ever settling into the intermediate states necessary for its accelerated progression. It collapses back to its previous state, much like the Zeno effect itself. There exists a sweet spot, a precise cadence of observation outside of which the effects falter. Another significant boundary arises with the sheer complexity and size of the quantum system in question. While a single beryllium ion can be remarkably isolated and controlled, a larger ensemble of atoms, or a more intricate quantum circuit, introduces a multitude of new interactions, both internal and external. Each interaction, however slight, contributes to decoherence, the insidious process by which a quantum system loses its fragile quantum properties and falls into a classical state. The Zeno effect acts as a shield against this decay, but it is an ongoing battle against the universe's inherent tendency towards classicality. As the number of interacting particles increases, the environmental noise amplifies exponentially, making it increasingly difficult to sustain the precise coherent states required for Zeno and anti-Zeno manipulations. The quantum world is inherently leaky, constantly spilling information into its surroundings, and no amount of measurement can entirely seal every possible exit. Furthermore, the strength and type of measurement play a critical role. A measurement is any interaction that transfers information, but not all interactions are equally effective or benign. Too weak an interaction may not cause sufficient wave function collapse to inhibit or accelerate evolution, while too strong an interaction can fundamentally alter the system in unpredictable ways, introducing unwanted noise, or even destroying the delicate quantum state. The quantum engineer constantly navigates this razor's edge, seeking the perfect balance between acquiring information and perturbing the system. Finally, practical and energetic limitations loom large. To continuously probe a quantum system with the speed and precision required for these effects demands incredibly sophisticated laboratory setups, cryogenic temperatures, and powerful, precisely tuned lasers or microwave pulses. These are not trivial undertakings. As we envision applying these effects to ever more complex systems, the energy requirements and technological overhead escalate, presenting a formidable frontier. The dominion of Zeno, while powerful, is not absolute. It is a meticulously earned control constrained by the intrinsic nature of quantum reality and the very practicalities of our interaction with it. This confrontation with limitation forces us to refine our understanding, moving from boundless wonder to a more nuanced appreciation of these profound quantum phenomena. For all our newfound dominion over the quantum realm, for all the astonishing control we exert through the Zeno and anti-Zeno effects, there exists a relentless, pervasive force that stands as quantum's mortal enemy. It is a silent, ubiquitous saboteur, constantly working to unravel the delicate tapestry of superposition and entanglement, erasing quantum information with insidious efficiency. This adversary is known as decoherence, and understanding its ceaseless work is paramount to truly comprehending the challenges and triumphs of quantum engineering. Decoherence is in essence the unavoidable process by which a quantum system loses its quantumness and succumbs to the classical world. We have learned that a quantum measurement is any interaction that transfers information about a system's state into a classical environment. Decoherence, then, is precisely this: the myriad ceaseless measurements enacted by the environment itself. Imagine a pristine, isolated quantum particle existing in its beautiful probabilistic superposition, a cloud of possibilities awaiting definition. This particle is not truly alone. It is constantly bombarded by stray photons jostled by atomic vibrations from its surroundings, buffeted by ambient electromagnetic fields, or subtly influenced by the thermal energy of its container, however cold. Each of these tiny, seemingly insignificant interactions constitutes an unsolicited peek by the environment. With every such interaction, a minuscule fragment of information about the particle's quantum state leaks out, becoming entangled with the surrounding environment. This leakage, this transfer of information from the quantum system to the vast, complex, and classical world around it forces the system's wave function to collapse. It loses its coherence, its ability to exist in multiple states simultaneously, and snaps into a definite classical state. This happens not because a human observer consciously decides to look, but because the universe itself, through its innumerable interactions, is continuously observing and defining the quantum system. For a qubit, the fundamental building block of quantum computation decoherence is the ultimate antagonist. A qubit's power lies in its ability to exist in a superposition of 0 and 1 simultaneously, and to be entangled with other qubits. But this exquisite fragility means that even the slightest interaction with its environment, a stray phonon, an errant electron, a temperature fluctuation, can cause it to decohere. The superposition vanishes, the entanglement dissolves, and the precious quantum information it holds collapses into a classical 0 or 1, rendering it useless for complex computations. It is why quantum computers require extreme isolation, operating in cryogenic refrigerators at temperatures colder than deep space, and why superconducting qubits are often housed in elaborate shielding. The Quantum Zeno effect, which we have explored as a protective shield, is a direct countermeasure against decoherence. By implementing rapid controlled measurements, the quantum engineer attempts to repeatedly reset the qubit to its desired state, collapsing it back to its initial coherent form before environmental interference can fully corrupt it. It is a perpetual race against time, a battle to outmaneuver the incessant random measurements that the environment imposes. The anti-Zeno effect, too, functions within this battleground, albeit by deliberately leveraging certain environmental interactions to hasten a desired transition rather than preventing decoherence. Ultimately, decoherence represents the universe's inherent tendency towards classicality, a fundamental friction that quantum technologies must always contend with. It is the inescapable price of interaction, the whisper of the macroscopic world imposing its certainty upon the probabilistic quantum realm. Overcoming or mitigating decoherence remains the single greatest engineering and scientific challenge in building robust, scalable quantum systems, a testament to the fact that while we learn to wield profound quantum powers, the universe always reminds us of its own deeper, unwavering laws. We have journeyed deep into the quantum realm, witnessing how observation in its multifaceted forms shapes reality, freezing the mercurial dance of probabilities into singular states. We have grappled with the profound question of collapse, that instantaneous snap of potential into actuality, and even wondered if consciousness itself plays a unique role in this cosmic act of definition. But the story of quantum reality is not a single linear narrative. It is a tapestry woven with threads of competing interpretations, each as mind-bending as the last. Now we are confronted with a radically different view, one that sidesteps the enigmatic mechanism of collapse entirely, yet expands the very fabric of existence beyond our wildest imaginings. Imagine, if you will, a universe where every quantum possibility, every potential outcome, is not merely a fleeting shadow until observed, but rather an equally real unfolding. This is the heart of the many worlds interpretation, a profound departure from the idea that observation forces a choice. Here, there is no mysterious collapse, no single reality being plucked from a myriad of possibilities. Instead, at every quantum juncture, at every moment of interaction or measurement, the universe itself divides, blossoming into an array of parallel realities. Consider the quantum particle existing in a superposition of states, perhaps both spinning up and spinning down simultaneously. In the traditional view, when we measure its spin, it collapses into either one state or the other. But in the many worlds interpretation, both outcomes occur. The universe in that instant bifurcates. In one branch, we, the observers, measure the particle as spinning up, and that becomes our reality. In the other, equally real branch, another version of us measures the particle as spinning down, inhabiting a universe where that is the truth. Our perception, our conscious experience, is simply of existing within one of these countless ever-branching realities. This concept pushes against the very bedrock of our classical intuition. We are accustomed to a singular defined reality where choices made lead to unique consequences and events unfold along a solitary path. Yet the many worlds view insists that every roll of a quantum dice, every decay of an unstable atom, every interaction that transfers quantum information into a larger system spawns new universes. We, the observers, are not collapsing the wave function. We are merely becoming part of one of the many waves continuing our existence in a particular specific branch, while uncountable other versions of ourselves diverge into different, equally valid timelines. This interpretation offers a compelling, if unsettling, solution to the measurement problem. If every possibility is actualized in its own distinct universe, then the perplexing question of why or how a wave function collapses simply vanishes. It doesn't. Instead, the entire quantum wave function continues to evolve, deterministically, endlessly, branching with each branch representing a distinct, non-interacting reality. Our experience of a single definite outcome is merely a consequence of our being confined to a particular branch, forever unaware of the myriad other branches that spun off into their own unique futures. The confrontation here is not just with a scientific puzzle, but with the very notion of our singular existence, our individual agency, and the seemingly solid ground beneath our feet. We find ourselves peering into an abyss of infinite realities, each a testament to the quantum realm's unfathomable capacity for possibility. We have explored the perplexing dance of quantum particles, from their mysterious superpositions to the dramatic act of wave function collapse. We have even contemplated an infinite branching of realities, where every quantum possibility unfolds into its own universe. Yet beneath these interpretations, a more fundamental, almost unsettling question persists: what precisely is the state of a quantum system before it is observed, Does it possess an objective reality fixed and independent, even when no one or nothing is looking? This question strikes at the very core of our classical understanding of existence. In our everyday macroscopic world, we take for granted that objects possess definite properties, whether we perceive them or not. The moon, we assume, remains spherical and luminous in the sky, even when clouds obscure it, or when every human on Earth is asleep. A chair in an empty room still has 4 legs, a specific color, and a certain mass. Its reality is objective, pre-existing, and seemingly independent of any interaction or observer. This is the bedrock of our intuitive universe, a universe where things simply are. But the quantum realm relentlessly confronts this deep-seated conviction. When we speak of a particle in superposition existing simultaneously in multiple states, a spin that is both up and down, a location that is everywhere at once, we are describing a reality that defies this classical objectivity. The wave function, that mathematical description of all possibilities, does not describe a particle that is in a definite state, but rather a particle that could be in any of several states. It is a cloud of potentiality, not a concrete entity. This leads to a profound philosophical confrontation. If the act of measurement, any interaction that transfers quantum information into a classical environment, as we explored earlier, is what defines a quantum particle's state, then what definitive qualities does it possess in the absence of such an interaction? Does the electron circling a nucleus truly have a precise position or momentum? Before we attempt to measure it, or does that precision only spring into being through the very act of inquiry? Many physicists aligned with the Copenhagen interpretation embrace this counterintuitive notion: a quantum system simply does not possess a definite reality until measured. Its properties are not merely unknown to us, they are intrinsically undefined. The electron is not somewhere specific before we look. It literally exists as a probability distribution across space. This is not a limitation of our instruments, but a fundamental characteristic of reality itself at the subatomic scale. It is a universe where reality is not merely revealed by observation, but in a profound sense created or actualized by it. This perspective challenges us to shed our ingrained classical habits of thought. We cannot simply imagine a tiny classical particle moving along a trajectory, even if we don't know its exact path. The quantum world insists that the path itself, or the state itself, is not defined until it interacts with something that measures it. To ask what is its state before measurement is akin to asking what color is an unpainted canvas. The question presumes a property that does not yet exist. For those seeking a universe with pre-existing objective properties, this quantum truth is deeply unsettling. It implies that the universe in its most fundamental aspects might not have a fixed independent reality waiting to be discovered. Instead, its attributes might only emerge through its interactions through the very act of its becoming observable to larger classical systems. The Quantum Zeno effect itself, by holding a system in a state through repeated interaction, highlights this dependence. Without the watchful eye of continuous measurement, the system would evolve and transform, its state becoming diffuse and undefined once more. So we are left to ponder, what is reality like when no watchful eye is cast upon it? Is it a ghost of possibilities, a shimmering potentiality awaiting actualization? Or is there perhaps a deeper hidden layer of existence that quantum mechanics has yet to reveal, where properties are always definite, only masked from our limited perception? This profound philosophical chasm between a universe that is and a universe that becomes through observation continues to be one of quantum mechanics' most enduring and captivating mysteries. It is a confrontation not merely with the strange behavior of particles, but with the very nature of existence itself. We have plunged into the perplexing heart of the quantum realm, where particles exist as probabilities, observations seem to sculpt reality, and entire universes might bloom from a single quantum decision. We have wrestled with profound questions. Does consciousness play a role? Does reality even exist when unobserved? Yet as we stand at the edge of this bizarre quantum landscape, a monumental chasm stretches before us, separating this microscopic strangeness from the familiar, predictable world we inhabit. This is the grand quest to bridge the quantum and classical, to reconcile the bizarre with our everyday experience, and to understand how the foundational oddities of the very small give rise to the macroscopic certainties of the very large. Our lives unfold in a classical universe. We do not observe cats that are simultaneously alive and dead, nor do our cars phase through walls. Chairs undeniably have a definite position, and the moon is always there, regardless of whether we gaze upon it. How then do the fundamental quantum rules, which dictate superposition and probabilistic existence, transform into the solid single realities of our ordinary lives? This is not merely a philosophical curiosity. It is a profound scientific challenge, a missing link in our understanding of the cosmos. The answer scientists increasingly believe lies in a process we have touched upon before: decoherence. We know decoherence as the quantum's mortal enemy, relentlessly erasing fragile quantum information and causing wave function collapse. But what if decoherence is not just a destroyer, but also the very architect of classical reality? It acts as the bridge, a tireless, ceaseless interaction between quantum systems and their vast, complex environments. Every quantum system, no matter how isolated, is perpetually interacting with its surroundings. Stray photons, air molecules, the vibrations of its container, even distant gravitational fields. Each of these interactions, no matter how subtle, functions as a form of measurement, albeit one distributed across countless environmental particles. As we defined, a quantum measurement is any interaction that transfers information about a quantum system's state into a classical environment. This means the environment itself is a continuous, pervasive observer. Imagine a single quantum particle in superposition existing in multiple states. As it interacts with its environment, information about its quantum state leaks out. This leakage is not a gentle trickle, but a cascade of entanglement, spreading its quantum possibilities across an ever larger number of environmental particles. As the number of entangled particles grows exponentially, the distinct quantum phases that allowed for superposition rapidly vanish. The system, to put it, simply loses its quantum coherence. It decoheres. This relentless environmental observation effectively forces the quantum system to choose a definite state, not through a conscious observer's intent, but through the sheer statistical weight of countless tiny interactions. The multiple realities of superposition are for all practical purposes averaged out, leaving behind only the classical outcome we perceive. A chair, for example, is made of trillions of atoms, each interacting with countless photons and air molecules every instant. The cumulative effect of these interactions is so rapid and pervasive that any superposition of the chair's overall state is instantly decohered, leaving it firmly in one definite classical position. The Quantum Zeno effect, which holds a system in a state through deliberate rapid measurement, becomes even more poignant in this light. It is a targeted artificial version of what the environment does naturally, but with a specific goal to preserve a quantum state from its natural decoherence and evolution. Conversely, the environment's unceasing random measurements cause decoherence, effectively driving quantum systems into classical states. The quest to fully understand this transition, this seamless emergence of classical reality from quantum bedrock, remains one of physics' greatest challenges. It demands a unified theory that can describe both realms not as separate domains, but as two sides of the same fundamental coin. Achieving this would not only complete our picture of the universe, but also unlock unprecedented control over matter and energy, potentially leading to quantum technologies that transcend our current imaginings. The tension between the probabilistic quantum and the deterministic classical drives scientific inquiry forward, pushing us towards a more complete and profound understanding of existence itself. We have journeyed far into the quantum depths, unraveling the bizarre tapestry of reality at its most fundamental level. We have witnessed how observation through the Quantum Zeno effect can impose stillness on the fleeting dance of subatomic particles, arresting their evolution, holding their delicate states indefinitely at bay. This astonishing power, the ability to seemingly freeze time for the very small, leads us now to confront one of humanity's oldest, most captivating dreams: immortality. Can the principles we have unearthed, this unprecedented control over quantum evolution, somehow extend to life itself, granting us a reprieve from the relentless march of time and decay? The concept sparks the imagination. If continuous observation can prevent a beryllium ion from changing its energy level, if it can protect a qubit from the ravages of decoherence and error, might it not in some distant future be applied to the complex, intricate quantum systems that constitute a living being? Could a sufficiently advanced form of quantum observation, a perpetual peeking at the fundamental building blocks of life, prevent cellular degradation, halt the accumulation of molecular damage, or even arrest the entropic processes that lead to aging and death? This is the ultimate question, the speculative precipice at the climax of our quantum journey. However, as with all grand aspirations born from quantum mechanics, we are immediately confronted by the stark realities of scale and complexity. We must remember the critical limitations of the Quantum Zeno effect, as we explored previously. It works most effectively on isolated, simple quantum systems. A beryllium ion is a single fundamental particle. A qubit, though more complex, is still a carefully engineered, cryogenically cooled, and electromagnetically shielded unit. A human body, by contrast, is a colossal symphony of trillions of cells each, a universe of molecules, atoms, and ceaselessly interacting quantum fields. The challenge begins with the very definition of observation, or measurement, in this context. For a quantum system to be frozen, information about its state must be continuously transferred into a classical environment. For a single atom, a precisely tuned laser beam suffices. But for a human body composed of something like 7 × 10⁻27 atoms, each performing its own quantum dance, what would constitute a measurement sufficient to halt its decay? Every single interaction, every photon that hits a cell, every chemical reaction, every internal process is a form of quantum measurement already occurring. And as we now understand, the relentless, omnipresent environmental observation is precisely what causes decoherence, driving quantum systems into classical states and paradoxically towards decay, not away from it. If we were to attempt to apply the Quantum Zeno effect to a biological system, we would need to continuously measure the quantum state of every critical component, every protein, every DNA strand, every molecule. This would require an unimaginable level of precision and energy far beyond any technology we can conceive. The measurement frequency would need to be astronomically high, exceeding the natural evolutionary rate of even the fastest biochemical reactions, let alone the gradual processes of aging. Such an intervention would be so invasive, so disruptive, that it would not merely freeze life. It would likely destroy it outright. Furthermore, life in its very essence is dynamic. It is a process of constant change, transformation, and interaction. Cells divide, molecules are synthesized and broken down, energy flows, information is processed. These are not static states. They are ceaseless evolutions. The Quantum Zeno effect works by preventing evolution, by repeatedly collapsing the wave function back to an initial state, inhibiting the accumulation of probability necessary for transition. To apply this to a living being would imply arresting all biological processes, preventing cellular repair, nutrient absorption, waste elimination, and even thought itself. This would not be life preserved, but life suspended in an eternal, lifeless tableau. It would be a stillness so absolute that it negates the very definition of being alive. The philosophical implications are profound. Is immortality truly desired if it means a static existence devoid of growth, experience, or change? The human quest for extended life is often driven by the desire for more time to learn, to love, to create, to be. Yet the quantum path to stillness, as implied by the Zeno effect, would offer an eternity of non-being, a frozen monument, rather than a continuing journey. While the Quantum Zeno effect has undeniably granted us unprecedented control over the evolution of individual quantum systems, stabilizing qubits for quantum computing, or enhancing atomic clock precision, its application to the grand complex and inherently dynamic symphony of a living organism remains firmly in the realm of science fiction. The scale, the omnipresent decoherence, and the very nature of life as a process of continuous change present obstacles that current physics indicates are insurmountable, at least with this specific mechanism. The tension between the profound, almost godlike control offered by quantum phenomena and the intrinsic messy reality of existence culminates here. The dream of eternal youth, fueled by quantum wonder, clashes with the very laws that govern the universe, reminding us that some boundaries for now remain uncrossed. Our speculative journey into quantum immortality culminates in a clear, sobering understanding, while the Quantum Zeno effect grants astonishing control over isolated quantum systems. The formidable challenges to applying it for indefinite cessation of decay in a living organism are for all intents and purposes insurmountable. We now unpack the sheer unyielding practical barriers that prevent such a dream from becoming reality. The first and perhaps most overwhelming obstacle is the sheer scale. We have observed the Quantum Zeno effect meticulously applied to single beryllium ions or superconducting qubits. These are microscopic entities, often cooled to near absolute zero and shielded from virtually all environmental interference. A human body, by staggering contrast, is a macroscopic entity comprised of an astronomical number of particles, far exceeding 1027 atoms, arranged in unimaginably complex and dynamic configurations. To observe every single quantum state within this colossal system, with the frequency and precision required to inhibit its natural evolution, would necessitate a measurement apparatus of unthinkable power and scope. It is not just about observing one quantum particle, but every relevant quantum particle simultaneously and continuously. This leads us to the second profound challenge: the inherent dynamism of life. The Quantum Zeno effect freezes a system in a particular state by repeatedly collapsing its wave function back to that initial state. Life, however, is not a static state. It is a ceaseless cascade of chemical reactions, energy transfers, and information processing. Cells divide, repair themselves, synthesize proteins, and undergo programmed death. These are all processes of evolution and change at a fundamental molecular level. To freeze these processes, as the Zeno effect would demand, would be to halt the very essence of life. It would be an indefinite cessation of decay, yes, but also an indefinite cessation of being. The system would be preserved but no longer alive in any meaningful sense. This isn't just a technical problem, it's a conceptual paradox. Life is change, and the Zeno effect prevents change. Consider, too, the invasiveness of measurement. Even the most delicate quantum measurements inevitably impart some energy or information to the system. While non-demolition measurements are possible for individual qubits, scaling this to a living being would require bathing every atom in a torrent of precise, targeted interactions. Such an intervention would itself be catastrophically disruptive. The very act of preventing decay through continuous measurement would likely cause immediate and widespread cellular damage, breaking down the intricate molecular machinery of life faster than any natural aging process. The sheer energy required to perform these constant ultra-high frequency measurements on quadrillions of quantum states would be astronomical, likely vaporizing the subject long before any immortality could be achieved. Then there is the issue of decoherence itself. We have learned that decoherence is the relentless environmental observer that pushes quantum systems into classical states. In a complex biological system, interactions with the environment are not just present, they are ubiquitous and essential for life. Every breath, every heartbeat, every ray of light, every chemical bond is an interaction that causes decoherence. To overcome this natural pervasive force, the artificial Zeno measurements would need to be infinitely more powerful and rapid than the sum total of all environmental interactions, an impossible task. The very bridge that connects quantum strangeness to classical certainty, decoherence, becomes the unyielding wall against this particular vision of immortality. Furthermore, the quantum Zeno effect preserves the initial state. Aging is not simply a decay from an initial perfect state. It is a complex process involving accumulation of errors, misfolded proteins, DNA damage, and the gradual decline of cellular repair mechanisms. To truly combat aging, one would need to correct these accumulating errors, not merely freeze them in place. The anti-Zeno effect, which can accelerate transitions, offers some tantalizing possibilities for guiding quantum evolution. But even that is about steering a system to a new state, not holding it in eternal stasis, while simultaneously allowing dynamic processes essential for life. In summary, the quantum Zeno effect, while a profound tool for quantum engineers stabilizing delicate qubits, is not a gateway to biological immortality. The formidable challenges of scale, the dynamic nature of life, the destructive invasiveness of required measurements, the immense energy demands, and the pervasive reality of decoherence solidify its limitations. We are left with the grounding realization that while quantum mechanics reveals incredible control at the subatomic scale, its direct application to indefinite life extension, using this specific principle, faces barriers that appear to be fundamental laws of the universe, not merely engineering hurdles. The dream persists, but the quantum path to it through the Zeno effect is impassable. Having grappled with the exhilarating yet ultimately unattainable vision of quantum immortality, we now firmly anchor our gaze back to the practical and astonishing reality of the quantum Zeno effect. If it cannot grant us eternal life, what can it truly deliver for humanity? The answer lies not in fantastical leaps, but in the painstaking, brilliant work of quantum engineers and theorists who are leveraging this peculiar phenomenon to forge the next generation of transformative technologies, shaping a future where the quantum realm is not just a mystery, but a tool, We have already seen how the Quantum Zeno effect acts as a protective shield for the fragile states of qubits, extending their coherence time. This is not merely an incremental improvement, it is a foundational pillar for quantum computing. Imagine a future where quantum computers, once confined to fleeting moments of calculation, can sustain complex operations for far longer durations. This amplified coherence directly translates into the ability to run more intricate algorithms to solve problems currently intractable for even the most powerful supercomputers. The Zeno effect, through rapid non-demolition measurements, acts as a vigilant guardian, constantly nudging qubits back to their intended states, actively suppressing the errors that threaten to collapse the quantum computation prematurely. This capability is not just an enabler, it is an accelerant for the quantum age. Beyond computing, the precision of our world is about to sharpen dramatically. We know the Quantum Zeno effect already enhances atomic clocks, keeping them from drifting and ensuring steadfast precision. But what about the next leap? We envision Zeno-stabilized atomic clocks becoming so accurate they could measure subtle relativistic effects on Earth, contributing to entirely new forms of navigation, or even revealing minute shifts in the Earth's gravitational field, offering unprecedented insights into geological activity. Quantum sensors, too, benefit immensely. By continuously suppressing environmental noise and maintaining the integrity of quantum states, the Zeno effect will yield cleaner, more trustworthy signals, enabling sensors so sensitive they could detect single molecules for medical diagnostics, probe for dark matter in the cosmos, or even map the brain's neural activity with unimaginable fidelity. The very fabric of our digital communications will be fortified. While quantum encryption already offers unhackable security, where eavesdropping instantly alters the quantum key, the Quantum Zeno effect promises to make these quantum communication channels more robust over longer distances and through noisier environments. By continuously monitoring the quantum states of entangled photons or other information carriers, the Zeno effect can protect them from decoherence during transmission, ensuring that the quantum link remains secure and viable for far more practical applications, laying the groundwork for a truly secure quantum internet. But the innovations do not stop there. We are glimpsing possibilities in areas as diverse as materials science. What if the Zeno effect could be used to stabilize novel quantum phases of matter, allowing us to engineer materials with properties currently beyond our grasp? Perhaps room temperature superconductors, materials that could revolutionize energy transmission and storage, or new topological materials with unique electronic properties for future devices. By holding delicate quantum states in place, scientists could explore and manipulate previously inaccessible phenomena, unlocking pathways to entirely new classes of substances. Furthermore, as a scientific tool, the Zeno effect offers a unique window into the quantum world itself. By actively preventing quantum systems from evolving, researchers can isolate and study the most fleeting of quantum phenomena, understanding the precise mechanisms of decay and interaction with unprecedented clarity. It becomes a quantum microscope freezing moments of quantum transition to reveal the intricate dynamics that govern the subatomic universe. The quantum engineer. Our modern scientist stands at the forefront of this revolution. They are the architects of these new realities, harnessing the bizarre power of observation to sculpt useful technologies. The vision is no longer about defying death, but about perfecting life through quantum understanding. It is about a future where computations are faster, measurements are sharper, communications are impregnable, and materials possess properties we can only dream of today. The Quantum Zeno effect. A seemingly abstract paradox from an ancient philosopher continues its profound transformation from theoretical curiosity to a cornerstone of tomorrow's most significant innovations. The quantum journey, it turns out, is just beginning, and its most exciting destinations lie firmly within the realm of the attainable. Having explored the extraordinary practical applications of the Quantum Zeno effect, from supercharging quantum computers to enhancing the precision of our most sensitive instruments, we now turn our gaze back to the effect's most profound and enduring legacy, its role in illuminating the deepest mysteries of existence itself. The Quantum Zeno effect is not merely a clever trick of quantum engineering. It is a fundamental probe, a tangible demonstration of principles that continue to challenge our understanding of reality observation and the very fabric of the universe. The Zeno effect, at its heart, serves as a vivid experimental confirmation of the active and transformative role of observation in the quantum realm. It shows us unequivocally that the act of measurement, any interaction that transfers information, is not a passive act of discovery. It is an intervention, a dynamic process that halts a system's natural evolution, forcing its probabilities into a single definite state. This challenges the very notion of an independent, pre-existing reality, compelling us to ponder anew whether quantum systems possess objective reality before interaction. The Zeno effect makes this abstract philosophical debate concrete, providing a laboratory setting where we can directly witness reality being sculpted by persistent inquiry. It also deepens our understanding of wave function collapse. While the many worlds interpretation attempts to bypass collapse by branching universes and decoherence, provides a mechanism for its macroscopic appearance, the Zeno effect offers a distinct perspective. It demonstrates that by merely looking repeatedly, we prevent the cloud of possibilities from spreading, maintaining the system in its initial state. This isn't merely about the particle not decaying. It is about the prevention of the probability wave evolving to accumulate sufficient potential for decay. This constant reset, this perpetual redefinition of the system's state, forces us to continually re-evaluate the nature of potentiality versus actuality in the quantum world. Furthermore, the Zeno effect intertwines intimately with the concept of information. For the effect to work, information about the system's state must be continually extracted and made accessible. This highlights the crucial link between information and physical reality at the quantum level. It suggests that the very act of knowing or having the potential to know something about a quantum system fundamentally impacts its behavior. This connection between the abstract realm of information and the concrete reality of particles remains one of the most fertile grounds for quantum research, and the Zeno effect provides a clear experimental window into this intricate relationship. The enduring philosophical inquiry into the observer's role is continually fueled by the Zeno effect. Whether consciousness plays a unique role, or whether any interaction counts as a measurement, the effect underscores that reality at its most fundamental level is not a given. It is emergent, dynamic, and profoundly influenced by its interactions. The Zeno effect, alongside its accelerating counterpart, the anti-Zeno effect, offers a tantalizing glimpse into a universe where evolution is not solely an unyielding force, but something that can be strategically controlled, halted, or even guided. This grants us an unprecedented level of control over the quantum world, pushing the boundaries of what we thought possible. Thus, the Quantum Zeno effect transcends its utility in quantum technologies. It remains a powerful lens through which we scrutinize the very laws that govern our universe. It forces us to confront the counterintuitive nature of quantum reality, to question our classical assumptions, and to continue the grand philosophical debate about the essence of existence itself. It reminds us that at the heart of the quantum realm lies not just complexity, but an elegant, profound simplicity waiting to be understood, a simplicity that reveals how observing the arrow, even briefly, can indeed freeze its flight. Even as the Quantum Zeno effect and its paradoxical sibling, the anti-Zeno effect, transition from theoretical curiosities to indispensable tools in our nascent quantum technologies, the fundamental questions they provoke reverberate through the halls of scientific inquiry. The very nature of reality, the role of the observer, and the meaning of measurement itself remain at the heart of a lively and evolving conversation among the brightest minds in physics. We are not at a static point of understanding. Rather, we stand amidst a vibrant, sometimes vociferous debate where established paradigms clash with audacious new ideas. For decades, the Copenhagen interpretation has held sway, postulating that a quantum system exists as a cloud of possibilities, a wave function, until the act of observation collapses it into a single definite state. The Zeno effect, by demonstrating how continuous measurement actively prevents the evolution of a quantum system, provides compelling empirical weight to this concept of collapse. It illustrates with chilling clarity that our persistent peaking can indeed freeze a particle in time, holding its fate in suspense. But then the anti-Zeno effect arrives, offering a counterintuitive twist. Strategically tuned observation can also accelerate a quantum system's journey towards a new state. These effects do not simply confirm a theory. They allow us to manipulate the very process of quantum evolution, deepening the mystery of what constitutes an observation and why it holds such profound power. This practical manipulation, however, only intensifies the philosophical confrontation. If measurement is merely any interaction that transfers information into a classical environment, as we have explored, does that diminish the role of consciousness, or does it merely abstract it? The debate around whether consciousness plays a unique and fundamental role as the ultimate quantum observer persists, a powerful current beneath the surface of the mainstream discussion. While most physicists lean towards a more materialist view of measurement, the Quantum Zeno effect, with its almost sentient, wakeful watchdog behavior, continues to fuel the more mystical interpretations, reminding us how deeply unsettling quantum reality can be to our everyday intuition. We observe the scientific community grappling with these profound implications. On one side, proponents of the many worlds interpretation argue that every measurement simply causes the universe to branch, with all possible outcomes occurring in different parallel realities. From this perspective, the Quantum Zeno effect isn't about freezing a single reality, but about continuously forcing our specific branch of the universe to align with a particular outcome, while other branches simultaneously unfold with different results. It's a mind-bending concept that sidesteps the idea of collapse by multiplying realities. Then there are those who champion objective collapse theories, proposing that wave functions collapse spontaneously under certain conditions, without the need for an explicit observer, perhaps due to gravity or sheer system complexity. The Zeno effect, in their view, becomes a means to suppress these spontaneous collapses by constantly resetting the system. The conversation is not limited to grand philosophical sweeps. It extends to the very details of how we interpret experimental results. What defines the frequency of measurement required to induce the Zeno or anti-Zeno effect? How do these effects scale with system complexity? The practical limitations of these effects, which we have confronted, feed directly into theoretical refinements, pushing scientists to develop more nuanced models of quantum classical boundaries. Decoherence, quantum's mortal enemy, is constantly factored into these discussions, serving as the relentless bridge between the bizarre quantum world and our seemingly stable classical one. The Zeno effect's ability to act as a protective shield against decoherence becomes a powerful empirical data point in understanding how our quantum reality manifests into our everyday experience. The dialogue is dynamic, evolving with every new experiment, every more precise measurement, every bold theoretical proposal. It is a conversation rich with respectful disagreement, rigorous testing, and an underlying shared wonder at the universe's profound mysteries. The Quantum Zeno effect and its inverse are not just physical phenomena. They are powerful lenses through which we continue to scrutinize the very fabric of existence, pushing the boundaries of what we can control and what we can comprehend. They are constant reminders that our journey into the quantum realm is far from over, and that the greatest discoveries often lie not in definitive answers, but in the enduring questions that continue to unfold before us. Our journey into the quantum realm, a hidden universe beneath the surface of our everyday experience, stands as a testament to humanity's unyielding drive to unravel the universe's deepest secrets. We embarked on this exploration, guided by ancient paradoxes and fueled by modern scientific curiosity, pushing the boundaries of what is observable and what is comprehensible. From the intuitive certainties of classical physics, we descended into a world of wave-particle duality, superposition, and the profound transformative power of observation, where reality itself seemed to flex and shift under our gaze. The Quantum Zeno effect and its intriguing counterpart, the anti-Zeno effect, mark not an end, but a remarkable milestone in this continuous quest. We have witnessed how the theoretical predictions of pioneers like Sudarshan and Misra, once mere mathematical whispers, materialized into tangible reality through the ingenious experiments of Weinland and his contemporaries. We have seen a philosophical thought experiment transform into a powerful tool protecting fragile qubits in the nascent age of quantum computing, enhancing the precision of atomic clocks, sharpening the acuity of quantum sensors, and fortifying the very foundations of digital communication through unhackable encryption. Yet even as we harness these effects, building new technologies that promise to reshape our world, the fundamental questions persist, echoing through the vibrant debates among scientists. What truly constitutes an observation? Is it the conscious act of a human mind, or simply any interaction that transfers information from the quantum to the classical domain? The Quantum Zeno effect, with its capacity to actively preserve a quantum state, lends empirical weight to the notion that our persistent interaction indeed molds quantum reality. Conversely, the anti-Zeno effect, by strategically accelerating quantum evolution, broadens our understanding of how deeply our interventions can influence the universe's most fundamental processes. These phenomena force us to confront the very nature of existence. Do quantum systems possess an objective reality before we observe them, or are their properties intrinsically undefined until measurement occurs? The Copenhagen interpretation. The many worlds interpretation. Objective collapse theories. These are not just academic musings. They represent humanity's collective struggle to reconcile the bizarre truths of the quantum realm with our ingrained classical intuition. Each new experiment, each refined application of the Zeno effects, provides another piece of the puzzle, a fresh perspective on the cosmic canvas we are attempting to paint. Our scientific conversation is alive, dynamic, and unburdened by the expectation of a single ultimate answer. It is a dialogue shaped by respectful disagreement, propelled by rigorous testing, and consistently brought back to the precipice of wonder. We continue to grapple with the limitations of our control, understanding that factors like measurement frequency, system complexity, and the relentless march of decoherence define the boundaries of what these quantum effects can achieve. The dream of applying the Quantum Zeno effect to biological immortality, for instance, swiftly collapses under the weight of such insurmountable practical barriers, grounding our ambition in scientific reality, while still allowing for imaginative thought. This ongoing journey, This continuous unraveling of the universe's secrets is the very essence of our cosmic awareness. Each discovery, no matter how small, expands our understanding of the intricate, interconnected principles that govern all of reality. It reveals the universe not as a static, predetermined stage, but as a living, evolving entity, responsive to the very act of our inquiry. The Quantum Zeno effect and its inverse are not merely chapters in a textbook. They are active participants in this grand narrative, powerful lenses through which we sharpen our focus on the very fabric of existence. They are constant reminders that our quest for knowledge is boundless, that every answer opens a new vista of questions, and that the greatest revelations often lie not in final destinations, but in the enduring spirit of exploration that defines us. Our journey into the quantum realm is far from complete. Indeed, it has only just begun. We look out, we observe, we question, and in doing so, we continue to expand the very boundaries of what it means to know. Our winding journey through the quantum realm has brought us face to face with the universe's most enigmatic truths, illuminating the fundamental principles that govern existence at its most microscopic scales. We began in the seemingly predictable world of classical physics, only to descend into a domain where intuition falters, where particles exist as probability waves, and where the very act of observation dramatically reshapes reality. From the ancient paradox of Zeno's arrow to the groundbreaking theoretical work of Sudarshan and Misra, and the experimental triumphs of David Weinland, we have traced the extraordinary path that led to the discovery and harnessing of the quantum Zeno and anti-Zeno effects. These phenomena, which allow us to either halt or strategically accelerate the evolution of quantum systems, are more than mere scientific curiosities. They are foundational pillars of emerging quantum technologies, serving as protective shields for fragile qubits, enabling unprecedented precision in atomic clocks, sharpening quantum sensors, and fortifying the unhackable integrity of quantum encryption. We, the collective observer, have learned not just to witness the quantum realm, but to actively engage with it, bending its rules to our will and extending the fragile coherence that underpins quantum computation. This marks a profound shift, transforming an abstract philosophical puzzle into a powerful lever for innovation. Yet as we conclude this particular exploration, it is crucial to recognize that the journey of discovery is an endless one. The Quantum Zeno effect, while a testament to our growing mastery over microscopic phenomena, simultaneously amplifies the profound questions that continue to challenge our understanding of reality. The vibrant debates among scientists about the nature of quantum measurement, the role of consciousness, and the very structure of the cosmos, whether it branches into many worlds or collapses into a single one, are far from settled. These are not signs of uncertainty, but rather the hallmarks of a living, evolving scientific conversation, where every answer unveils a new stratum of inquiry. The universe in its boundless expanse and infinite complexity forever awaits our gaze. We have peered into the quantum realm, controlled its fleeting moments, and begun to decode its hidden language. But what other paradoxes lie waiting to be unearthed? What entirely new phenomena beyond our current imagination will surface as our observational tools become ever more refined and our theoretical frameworks ever more encompassing? The quantum Zeno effect itself might prove to be but a single facet of a larger, yet to be revealed principle, a stepping stone to even more audacious discoveries about the universe's operational code. Our continuous unraveling of the universe's secrets is the defining characteristic of our cosmic awareness. Each insight, from the most esoteric quantum effect to the grandest astrophysical revelation, contributes to humanity's expanding consciousness of its place within the cosmos. We are driven by an insatiable curiosity, an innate desire to understand not just what exists, but how it exists and why. This relentless quest transcends the immediate practical applications of our discoveries. It speaks to a deeper yearning for knowledge, a fundamental aspect of the human condition. So we turn our gaze towards the horizon, knowing that the quantum realm, with all its counterintuitive elegance, holds countless more secrets. The questions we ask today will undoubtedly be dwarfed by the questions that will arise tomorrow. The universe does not offer final destinations, but an endless vista of new frontiers beckoning us onward. We observe, we measure, we theorize, and in doing so, we perpetuate the grand unfolding narrative of human understanding, a narrative where the greatest revelations often lie not in definitive answers, but in the enduring, exhilarating pursuit of them. The universe remains infinitely complex, exquisitely strange, and forever poised, awaiting our eager, persistent gaze. The universe then does not merely exist, it persistently unfurls under the transformative power of our gaze. If the universe's persistent unfurling under the power of observation continues to captivate your mind, then join our journey of discovery on Astro Horizons. Subscribe to Astro Horizons for more captivating journeys into the universe's deepest truths. Which quantum revelation resonated most deeply with you?